Welcome back, and we are continuing our discussion. We've been talking about the AC response of an RC circuit, and we've been talking about complex impedance, and now we're going to do the same analysis with a LR or RL, an inductor and a resistor. And again, we're going to use what we've learned about rectangular coordinates and polar coordinates and phasors to kind of do the analysis. So let's just jump right in and start working on it, all right? So let's get our drawing program up here. All right, so what I'd like to do is let's try doing something where we kind of simultaneously do a couple things at once. This will be fun. All right, so let's first put up the circuit that we want to kind of analyze using our techniques for phasors, all right, in complex impedance. So let's go ahead and we're going to put an AC source, and let's put a resistor, and we'll put an inductor. All right, we'll close that off and complete the circuit. So we've got this R and we've got this L. And now, since we've got a signal generator, we can kind of change whatever this value is. But since we're going to do one computation here, we are going to say, let's see here, how about we do, let's say that we've got an RMS values of the voltage, an RMS value of, so let's do voltage equals 7.07. And so we'll say V equals 7.07, and that's RMS. And again, the frequency can be anything we want, but we'll say, just starting off, we'll just say it's 100 hertz for calculations. Now, the reason I say 7.07 is because the particular signal generator that we're going to do the develop the circuit on that we want to play with, it has a maximum peak voltage value of 10 volts. So that means the RMS would be 7.07, or excuse me, 0.707 times 10, which would be 7.07 volts. So that's why we're just setting that value there, just so that we can kind of mimic what we do here in the circuit on the bench there. All right, so here's one circuit. Now, what I also want to do is draw another circuit, which is similar, but we're just going to change a couple things here. So we're going to put the same generator. We're going to have the same values, so we're not going to copy them here. And then this time, we are going to put the inductor here, and then we're going to put the resistor here. All right. And so there's our resistor, there's our inductor. And in both cases, we're going to look at a couple voltages here. We're going to look here, right? Say this node here, and this would be, in this case, would be the voltage over the resistor. In this case, would be the voltage over the inductor. All right, and then we're also going to look differentially. So let's draw these as just dots, a little easier. All right, draw those as dots. And so we're going to look at the voltages across the resistor and the inductor in both cases. Now, one thing I want to bring your attention to is right off the bat, you can see that these are both like voltage dividers. So there's like a voltage divider kind of action going on here, right? And in both cases, if we think of these values, the R and the L, in terms of impedances, right? So we've got, ZR here, we've got ZL here, and then over here, we've got ZL here and ZR here. All right, and so now this is just the voltage divider, right? So the voltage over, say, the inductor would be ZL, right? So if we just wanted to know the voltage over the inductor here, right, that would simply be ZL over ZR plus ZL times whatever the input is. And as a matter of fact, we'll just leave that as V instead of a V, and we'll just call it V. All right, and so that would just be times V. and that's what would be the voltage over the inductor. And the reason why we can write that is because we're doing this all in complex impedance terms of Z. So these are voltage dividers. Both are just voltage dividers, all right? So let's start writing down what we know here, all right? So let's write down what the inductive reactance is, all right? So let's write down what the inductive reactance is, and let's set some values here. So I'm going to say that R equals 200 ohms in both cases, and L is going to be 2.2 millihenries, all right? And again, the values are both the same in both circuits. I'll just copy them over here. 2.2 millihenries, not micro, milli, and then this is going to be 200 ohms. All right, so one interesting thing is here is when you start working with inductors, the thing that you figure out real quick is inductors, the values that you're going to get commonly are going to be in microhenries or maybe millihenries, and it's really hard to make circuits that do anything at low frequencies. So in other words, you're going to have to get into real high frequencies when you start playing with inductors. So in this case, the resistor that I'm picking, 200 ohms, I'm picking that on purpose, and I'm selecting that value for a couple of reasons. Once we compute the inductive reactance here, you're going to see that the inductive reactance is pretty low until we get the frequency up pretty high. This 100 hertz has to get pretty high. And so we want to be able to affect this 200 ohms in a voltage divider like action. So we want to go from 0 to say 1,000 ohms of inductive reactance over some frequency range that's reasonable so that we don't have to go up into megahertz, right? And so to do that, we're going to get inductive reactance at some frequency, and it's going to have some value. The lower I make the resistance, the larger that inductive reactance will seem to that resistance as we make the resistance low, because we're trying to create a voltage divider action out of this circuit so we can see it. So if we pick a very large resistor value, like 20K or 100K, we're never going to get 100K ohms until we get up into mega or gigahertz of frequency. So I picked a fairly large, fairly small resistor in this case. Now the other thing that's important is when we put this on the signal generator, if we pick too small of a resistor, the signal generator won't be able to drive the circuit and too much current will flow. So we've got to kind of balance things. So again, you got to balance things if you want to get things to work on the bench and to be able to experiment with them. In simulation, we can do whatever we want, but on the bench, we can only do certain things with certain equipment. All right, that said, let's just get in here and let's start doing this. All right, so let's go ahead and let's calculate what x sub c is, and it's the same in both circuits. So x sub L, what's the equation for that? 2 pi FL, all right? And since I just mentioned x sub c, what's the equation for that? It's 1 over 2 pi FC, right? But we don't have that, so we're not going to use it. We don't have any capacitors. All right, so it's 2 pi FL, and our frequency is 100 hertz here. All right, so x sub L equals 2 times pi times 100 times our inductance, which is 2.2 millihenries. All right, and let's go ahead and let's everyone get their calculator out. Let's do it. 2 times pi times 100 times 2.2 millihenries is 1.38 ohms. All right, 1.38 ohms. 1.38 ohms. All right, and let me do that again just to make sure, and you check it again. 2 times pi times 100 times 2.2 milli. All right, 1.38 ohms. All right, and so that's at 100 hertz. Okay, at 100 hertz. Now, because the equation here is completely linear, if I double the frequency, right, then I'm just gonna, this would be like 200 hertz, right, 200 hertz, then this resistance would double. Seem reasonable? So it's linear. So at 100 hertz, it's this, all right? So at, we'll say equals, at 1,000 hertz, it would be 10 times this, right? So it would be 13.8 ohms at 1 kilohertz. Right? and then it would be, again, times 10, so it would be 138 ohms at 10 kilohertz. All right, so hopefully that's reasonable. So you can see at 10 kilohertz, we've got roughly what our resistance is here, right? Obviously a little bit less, all right? And then we could say, we could go to 100 kilohertz, but that's going to be problematic with the equipment. So why don't we just now double that to 20 kilohertz, all right? So at 20 kilohertz, it'll be 2 times that. So again, let the calculator do arithmetic. 276. So equals 276 ohms at 20 kilohertz, okay? So here are different ranges that we could set the frequency at and get different values at. Now, what we're going to do is we're just going to do all these calculations right now for this one value right here, right? But we know we could do them for all of these, and this is how things would go. All right, so first thing, let's talk about what the complex impedances are of each thing. All right, so again, both circuits are the same. We're going to do the left one, and then I just want to talk about the one on the right. All right, so over here, if we want to write Z sub R, right, the real part is 200 ohms, so it's 200 ohms plus 0J, right? Okay, and the complex impedance for the inductor is what? It's simply 0 plus X sub L times J. All right, and we know what X sub L is here at this particular frequency of 100, right? It's 1.38, so we're going to put it in there. So this equals 0 plus 1.38 J. Now let's be careful here for a moment. In the capacitor example with the reactance of the capacitor, remember the capacitor had a minus J, and the reason why is because it's X sub C equals 1 over 2 pi FC, and there was a minus J. And then if we go and we look at the phasor diagram real briefly here, if we can draw a straight line, if we look at the phasor diagram of the impedances, we would get, so let's say that the resistor, right, we'll make that one yellow. Hopefully you can see that. All right, so here's the resistor, here's its impedance, right? It's right on the real axis, right? And remember, this is the real axis right here, and then this is the plus J, and then this is the minus J. So the inductor, right, those always have a positive J, right? They're going up this way. And the capacitor has a negative J, all right? So this is X sub C goes this way, and X sub L goes this way, all right? So when you have the phasor diagram, you can kind of remember that. So we've got a plus J here and a minus J there if it's a capacitor, and a plus J if it's an inductor. So that's where that's coming from right there again, all right? And so now the impedance for the inductor is 0 plus XL sub J, and for the resistor is 200 plus 0J. All right, and these impedances are measured in ohms, no matter what. All right, so now we have those things, and so now let's talk about the voltage here. So remember, we can write this in both polar and rectangular form. So the magnitude of it, in this case, it's an RMS value, but we're going to first write it as a phasor. So we're going to say that V equals, and its magnitude in this case, and we're not talking using the word magnitude to represent if it's a peak value or an RMS value or this or that. We're just talking about in phasor nomenclature, notation, the first number is the magnitude of the signal. In this case, it's an RMS signal, so we know that, but when we use the word magnitude, we don't mean we're talking about the sine wave magnitude, we're just talking about the magnitude of the phasor. All right, so in this case, it's 7.07, all right, and we can put V for volts there if we want, but it gets a little confusing because we're calling this V, all right, and so we'll put the little V there, and then we're going to put our angle here. And now remember, we get to pick something as a reference. So we're going to pick the voltage as a reference. So we're going to put 0 degrees. If we wanted to put this in rectangular form, right, it would be simply this. It would be 7.07, right? and plus, and then there's no imaginary component, so it would just be 0J, right? And this, again, this whole thing is volts, right? So you can put the V right there. All right, so 7.07 plus 0J. So we've got both formats there. Now, same thing here with the ZR, right? The ZR, again, is in rectangular coordinates right now. If we wanted to put it into the polar coordinates, the magnitude of it, it's 200 plus 0, so the magnitude is just the 200. There's no component in the other axis. So that would be 200, and you know, we can put ohm here. And the angle, right, is just 0 degrees. This is right on the real axis, right? It's only got a real part, so that's what it would seem. And then now the impedance for the inductor, it has no real part, it's purely imaginary, and it's in the positive J. Okay, so let's be careful here. So first, what's its magnitude? Its magnitude is just this 1.38, 1.38, and again, this is in ohms. All right, and it's pointing in the plus J. So what is that? That's 90 degrees, right? That would be the angle. And then this, if it was down here, it'd be minus 90. So this is plus 90 degrees. Okay, so that's it. We know everything there is to know about this circuit, about the components at least. So now let's start doing some calculations. All right, let's put some of our famous pieces of information up here. So what do we know? Let's put Ohm's law, and V equals I times R, but we're doing the new Ohm's law, which is, or the modified one for complex impedances, or just for impedances, impedance in general. And remember, impedance is the it's the opposition to change in current, change in voltage, and remember, it's complex and it's for AC. So when you're talking about impedance, you're talking about AC circuits. An AC circuit can have a frequency of 0, though, so you can always use the word impedance if you like. But typically, impedance is for AC circuits, and it's a complex number which has a real part and imaginary part. So this is the equation right here. We're using V equals I times Z. And now we can figure out whatever we want to figure out. So why don't we first figure out the I in the circuit, so the general current in the circuit. And remember, the current's going to flip back and forth. One time it's going to, at one phase, it's going to go this direction, and then it's going to flip back and go that direction, all right? Doesn't matter. All right, so let's figure this out. So based on our formula up here, we have I equals, all right? And so I would equal V over Z. All right, so what do we need? We need the Z here, so we need the Z total. So we can compute what the Z total is very easily. So we want V over Z total. So to do this, we have V, that's right there, right? But we need Z total. So to do that, we simply need to add up our two complex impedances for the resistor and for the inductor. Okay, so that's easy to do. So Z total equals, what does it equal? It equals ZR plus ZL, all right, which, why don't we, let's do it right here. So ZR is 200 plus 0J. And since we're doing addition, we're going to use the rectangular format. If we're multiplying, we would use the polar format, but the rectangular is better for addition. So what do we have? 200 plus 0J, 200 plus 0J, all right. And then I'm just going to put a plus here, if that's okay with you, ZL, which is 0 plus 1.38J. And just so I can put them under each other in column form. 0 plus 1.38J. All right, so we add these two things together. What do we get? We get 200 plus 1.38J. All right, so again, we've got two different values here. One is in the real axis and one is in the imaginary axis. So again, if we wanted to kind of look at these over here. So here was the, over here in the phasor diagram. So the real part contributed this over here, and then the imaginary part contributed this over here. So we're going to want whatever the result is of these two things. And we've got a 200 against the 1.38. So in reality, the resistance is very, 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 very long. It's like that. And then the inductance is this little tiny short thing right here. All right, so then when we find the result of these two things, it's going to be, skewed towards the real part. All right, so keep that in mind. Okay, so now this is the rectangular format of this, but we want to do a division. So what we need to do is we need to put this into a polar format. All right, so here's our z total. All right, and so first we need to find the length of this. So we find the square root of the square of each of the components. All right, so we want to do 200 squared plus 1.38 squared. All right, and that's the magnitude. So we've got 200 squared plus 1.38 squared. All right, and then we'll take the square root of that, and that's 200.004. So as I said, it will have this 1.38 at this frequency has very, very little effect. All right, so for all intent purposes, it's 200. All right, so it's 200 as far as we're concerned. 200, and then the angle here, the phi angle between the imaginary component and the real component is again, or between the hypotenuse, right, which we just computed the length of that hypotenuse, this angle in here, phi, right, is going to be very, very small. So what's that again? So phi is the inverse tangent, remember that, it's the inverse tangent of the imaginary part over the real part. Imaginary part over the real part. Let's put that in a different color. All right, so we're going to say 1.38 over 200. All right, so let's go ahead and do that. So get your calculator out. We're going to do tangent inverse of 1.38 divided by 200. All right, and that equals 0.39. So it's like literally not even a degree. Okay, so we're going to say that this is 0.4 degrees. This is tiny. So our final phasor is 200 and 0.4 degrees for z total. But it's a positive angle, so that means that the final result of this is in this first quadrant right up here, so it's slightly inductive at this frequency. So at this frequency, the frequency is so low, the inductor is really not doing anything, and we can see that because the inductor at this frequency only has an impedance of 1.38 ohms, right? But if we were to increase the frequency to 1K, right, then it'd be 13.8, and to 10K it'd be 138, and to 20K it would be 276, and so on and so forth. So that's what I want to bring your attention to, is that the inductor it's a frequency dependent resistor, and its impedance goes up obviously linearly with the frequency. All right, so let's continue with our calculation here. So we wanted to figure out this. All right, so the current, so we need V over ZT. What's V? It's this value here, 7.07, and we have an angle of 0, and then over over our final value here, which is 200, and then an angle of 0.4 degrees. All right, so clearly this is going to be a very little effect on it, that angle, for example. Okay, so we're just going to divide the top by the bottom, so that's just 7.07 divided by 200. All right, and so that is 0.035, so let's say 35, let's just say 35 milliamperes. So 35 milliamperes. And the angle is just 0 minus 0.4, so it's a negative 0.4, 0.4. All right, so that's what our I is. Okay, so why don't we write this down again here so we can say that I in the circuit equals 35 milliamperes at an angle of negative 0.4 degrees. All right, so we can see that we have a good current, but we have a very small angle here. Now if we want to find the voltages over each of these things, we can. Okay, all right, so if we want to find the voltage over the resistor, okay, voltage over the resistor is going to be the current times its impedance. So voltage over the resistor, so is going to be I times ZR. All right, and then the voltage over the inductor is going to be I times ZL. All right, so let's go ahead and do that. And again, let's do it using the polar form because that is what we want to multiply and divide things in. All right, so what's the current again? So it's 35 and negative 0.4, so let's write that down. So 35 milliamperes at an angle of negative 0.4. Let's put some parentheses around that. And then same thing here. It's 35 milliamperes at an angle of negative 0.4. All right, and then times times the ZR. So ZR, if we look at its phasor up, it's right here. It's 200 and 0 degrees. 200 ohms, 0 degrees. All right, and then ZL, where is our ZL? It's right here. It is 1.38 ohms and 90 degrees. 1.38 ohms and 90 degrees. Make sure that 90 degrees. All right, so let's bring this down here and let's do the calculations. So VR equals and VL equals. So get your calculator out. So remember, we're going to multiply the magnitudes. 35 times 200, we're going to add the angles, multiply the magnitudes, and add the angles when you do multiplication. All right, so here we go. So 35 milliamps times 200 is 7. So we're going to get 7 volts here. And why don't we'll put 7 volts. And then the angle is simply this angle plus this angle, which will still be negative 0.4, negative 0.4. All right, and VL, same thing, 35 milliamps times 1.38. 35 milliamps times 1.38 equals, and in this case, we get a very, very small voltage here, so we can put this, do one more time here, make sure we got this right, 35 x3 times 1.38. We're getting millivolts obviously here. All right, so 48.3 millivolts, which is what you would expect, 48.3 millivolts. And what's our angle? It's negative 0.4 plus this 90 here, right? So basically it's going to be 89.6, right? So it's going to be 89.6. So that's it. So those are the voltages. Here's the current. Here's the current. Here are the voltages. Here are the impedances. And that's what the circuit is doing at 100 hertz. So it's not very interesting at 100 hertz. If we crank this up to 20 kilohertz, it gets very interesting. And we could do all these calculations again, but they're so tedious, it's better to simulate it. Now, what I want to bring your attention to was at 100 hertz, this inductor does not do anything. All right, so it has almost no impedance. So at 100 hertz, it has no impedance. So let me just kind of do this. If I were to take an output right here, and if I were to call this V out and do the same thing right here, here's V out. And then the input is like V in, that's the input, and here's where we're taking the output. So in both cases, we're going to take the output over this, this node to the right. In this case, there's an inductor. In this case, there's a resistor. Okay. So let's do this slow. So at low frequencies, this inductor has no impedance. It's for a short for all intent purposes. So there's nothing dropping over it. All right. So at low frequencies, V out is very small. It's negligible. Right. It's nothing. So at low frequencies, this is blocking this. All right. So at low frequencies, this is blocking this. Now, at high frequencies, this inductor is going to start having a lot of impedance. And since it has a lot of impedance, its resistance is going to go up like to 276 or higher. A lot of the voltage will drop over the inductor, which is where we're taking the V out at. So this circuit over here on the left, it's a high pass circuit. This is going to pass high frequencies. So the higher the frequency goes, the more inductance, the more reactance this inductor has, which means the more impedance it's going to have, and a larger voltage is going to drop over this. So we're going to get a bigger signal out as the frequency goes up. Now, on this circuit right here, right on the right, let's do the same analysis. Okay, so at 100 hertz, this inductor right here has almost no impedance. It's got 1.38 ohms, right? 1.38 ohms. Compared to this 200, it's like 1%, right? It's less than 1%. So the resistor drops all of the voltage. So we're getting this big signal over this resistor at low frequencies. All right, so we keep raising the signal up and up and up and up, and then finally, say at 20 kilohertz, now this impedance here of the inductor is 276. It's a little bit more than the resistor, so now we're only going to get about 40% voltage drop over the resistor, so it's lowering, lowering, lowering. So this is a low-pass filter. This will pass low frequencies, and this is a high-pass, okay? And in the next lecture, the next whole lecture where we're talking about a new subject, we're going to go through high pass and low pass where we're not going to have a fixed frequency here anymore. We're just going to talk about this as an F, as a general variable, and we're going to do similar kind of calculations, but we're going to do them so that we can generalize this and not just do one calculation at one frequency. So we're not going to be using these formulas for that case. We're going to use a different methodology. All right, but anyway, I wanted to show you this so you can kind of see it. Okay, so now the next thing that I want to do is I want to take what we've learned right now and let's go to the simulator, and we're going to go simulate this, and then we're going to build it. All right, so we're going to simulate and we're going to build it, and we're going to talk about a couple little gotchas and problems with building things that have inductors and measuring them with equipment that's not very expensive. So anyway, so let's go ahead. This is a good place to stop. Again, take a little pause, catch our breath, and we're going to come back and we're going to go ahead and do the simulation and then build the circuits and see if we can get this thing to work. Okay, so I'll see you in the next lecture. Bye. All right, welcome back, and we just took a brief pause there to pick up in the same material. So we're going over the LR circuit or RL circuit, AC, steady state response, and we've done all our calculations, and so let's kind of circle a few things here to make sure we've got everything. So we've got our ZR and ZL were calculated here, and then from that we calculated what the current was, and it's 35 milliamperes, give or take, and a phase angle of minus 0.4 degrees. Very small phase angle, very small, because at 100 hertz the impedance of the inductor is so small. And then we calculated what the voltages over the resistor and the inductor were, and 35 and 35 milliamperes phase angle times the 200 ohms at 0 degrees and 1.38 ohms at 90 degrees. And we came up with 7 volts and minus 0.4 degrees and 48.3 millivolts at 89.6 degrees. All right, so we figured everything out. And again, if you go back through here and look at everything, for example, if we look at the phase angle of the voltage, it's 0 degrees. And then if we look at the phase angle of the voltage on the resistor, it's 0 degrees. All right, and then if we look at the, let's see here, let's see something interesting. If we look at the inductor here, the final, excuse me, sorry, the on the voltage on the resistor is down here. We've got minus 0.4, and so if we look at that angle right there, minus 0.4, and then we look at the current, minus 0.4. So the current and voltage across the resistor are in phase, right? And the angle happens to be 0.4 negative. All right. But if we look at the inductor, it's got an 89.4, all right, and then the current has got minus 0.4, and if you look at the difference between those, you've got 90 degrees. So again, the current and the voltage in the inductor must be out of phase 90 degrees, and remember, we've got ICE is one of them, all right, so current leads the voltage in a capacitor, so current, and this stands for capacitor, and this stands for voltage, so current leads the voltage, so that's not the one we want, so it's LE or Eli. Voltage leads the current, so the voltage leads the current in an inductor. That's what the L is for, and C is for capacitor. All right, so now what we want to do is we want to go to our simulation. We're going to build a 200 ohm, 2.2 millihenry circuit of this configuration right here. And then we better get something about 7 volts and about 48.3 millivolts is what we're looking for here, all right? And we can't really see, we could extract out the phase angles if we really wanted to, but it would be painful. And the current is 35 milliamperes and some change either way. All right, so that's what we're looking for. So let's go ahead and go to our simulator. All right, so This is a Proteus again, and this is a piece of software that I use. It's a high-end CAD program. We're going to, of course, be using Circuit Maker when we do our layout because it's a free piece of software, not open source necessarily. In fact, it's closed source, I'm pretty sure. We'll be using Circuit Maker, but it does not have simulation. So again, we use Proteus because it's easy. You don't have to follow along if you don't want to. You can just watch what I do, but I would prefer if you did. And if you recall, you can just simply go online to labcenter.com. It's a UK company, United Kingdom company. You can download the free version of this here someplace in order and pricing. It's someplace in here. And then get a free version of it that you can use. It'll do simulation, all that, but you can't save, and there's a bunch of other things you can't do in it. But you can at least follow along with the simulations if you like. All right, so I've already built this, and what I'd like to do in this case, again, we're going to have a hard enough time learning Circuit Maker so that I don't want to confuse you with other tools. But this is so simple to use. I don't know if simple is the right word, but in this case, it's not that hard to build this circuit. So first, let's just run the simulation. Let's see that we match our results, and then we're going to actually build this, rebuild this circuit. Of course, you can get this circuit inside of the assets for this lecture and for this section, so you can look inside of that in the class materials and get it, so you can always get it, so don't worry about that. But we're going to rebuild this, which will kind of be fun, so you can kind of see how this goes. All right. Okay, so let's take a look here. So we've got our 200 ohm resistor. We've got our 2.2 millihenry inductor. We've got the same kind of structure. Then we've got some instrumentation. I've got a voltmeter here at the input. I've got a voltmeter across the resistor. Then I've got a current meter in line in the circuit. And then I've got a voltmeter across the inductor. Now, one thing I want to really bring your attention to is in this case right here, I want the voltage across the resistor. I don't want the voltage from the resistor to ground. That would be this, and that would just be the input. I want it across the resistor. To do this, I need to be able to have a floating differential instrument. And by differential, I mean there's 2 points. There's point 1 and there's point 2, and I can put it on there and get the voltage, right? This is the same thing in the real world. When you want to get the voltage on something, you need a differential input, unless everything is in reference to ground. And so that's why meters are good, multimeters, digital multimeters, because they have 2 probes. You can put it on top of a component and get the voltage across it, all right? Or you can put it into a circuit and get the current in the circuit, right? But if you're using an oscilloscope, you've got a little bit of a problem because the oscilloscope has a probe, and that probe is one input, but the other input is ground, and all the grounds are tied together. So you can only have one reference ground, all right? So you can get a differential probe, if you like, that are very expensive. That takes that one signal, splits it into 2, gets 1 voltage, and then brings it back to the single probe tip. So you can do that. So just be aware when you're measuring things, make sure you want to measure them either differentially or single-endedly relative to ground. All right, so that's it basically. This is an oscilloscope, a little digital virtual oscilloscope. We're going to look at the input, and then we're looking at the voltage across the inductor to see if we can see the phase angle. And then we've got an AC source. So again, this is a very Windowsy Windows program, and it's getting more and more so. Many CAD programs they feel like they're DOS with Windows on top of it because they're very old and they iterate them over decades sometimes. So this doesn't do what you would expect in a lot of cases, and many of these CAD programs do not. So when you click things and stuff, things don't do what you would think they do. So a lot of times, try right-clicking, try left-clicking, try dragging with the right, try dragging with the left, and then sometimes you kind of figure out how to get something. You're like, how do you move this? How do you select it? Anyway, so I'm going to right click on the icon on the graphic here, and it brings up the signal generator properties. AC source, just the name. We want sine wave. All right, and then we're setting the amplitude to 10, and the reason why is because in the other example, in our example, we set the RMS to 7.07. See that? Amplitude 10 is the same as RMS 7.07, and 100 hertz for the frequency. And that's basically it. Let's run the simulation. We go down here. There's run, forward, pause, and stop. And what we're looking for is we're looking for 7 volts, 50 millivolts, and 35 milliamps as the current. Okay, so let's see what we see. Here we go. Run the simulation, and it's running. And that's it. The simulator is caught up. And so let's see. Well, we got 35 milliamperes, so that's good. So that's our first thing. We're looking for 35 milliamperes. Great. And over here, we're looking for about 7.07 volts. And sure enough, over here, we've got 7 volts. And if we did all the decimal places, we would have got almost identical results. All right, and then we've got 0.05, right, volts here. And that's our exact value here. We've got, where is it, 48.3 millivolts. And we can stop the simulation. Since we know we're measuring millivolts, we can double click this and go to its properties and see it's in volts here. All right, and we can change that to millivolts and be a little bit more accurate to our math, I think. Let's see, and let's go ahead and run the simulation. And there we go, 49.6 millivolts, and we had 48. What do we have? 48.3 millivolts. All right. So as far as I'm concerned, this is exactly correct. And all right, and then we can look at the oscilloscope, and what we're looking for, we should see a bit of a phase angle between the source and the inductor voltage, right? So first, so I think the yellow line is the source, all right? So first, you know, your guess is as good as mine. Every time I use this, I got to figure it out. So channel A, we're going to increase the gain on it, all right? And there you can see the signal getting bigger. On channel B, which is the inductor, we're going to do that as well. Okay, and then we're going to change the frequency here. We're going to drop it down so we can see this. Okay, now we're going to drop this down. So now we're starting to see what's going on here better. All right, drop this down. Okay, and then slow down the frequency. There we go. All right, and what we see here is exactly what we expect. So this is really nice. So let me turn up the amplitude just a little bit, the gain, and let me slow down the frequency just a little bit. All right, so remember, right now the source and the voltage across the inductor should be 90 degrees out of phase. All right, and sure enough, if you look at this, they're 90 degrees out of phase. You know, if you were to scale this, they're 90 degrees out of phase in this case. And the reason why they're 90 degrees out of phase, they're actually, what is it, 89 point whatever, 89.6. The reason they're 89.6 is right now the circuit is acting purely resistive in this case. When the circuit starts getting purely inductive, when a circuit starts getting purely inductive, then that phase angle will get smaller again. We'll go back towards zero. But right now we've got nothing dropping over this inductor. All right, so this voltage between here and here has this 90-degree angle. So now, now we can quickly change this, right? So if we go to the math here, we saw that as we increase the frequency, we're going to increase the impedance, the inductive reactance, and then by the time we hit 20 kilohertz, we're going to have 276 ohms, which is greater than this resistor. So at 20 kilohertz roughly, we should be splitting this, you know, 60-40, right? 60% of the voltage should be over the inductor and maybe 40% over the resistor. All right, so let's see if that's true. All right, so let's set it to 20 kilohertz. Put that there for a second. We'll stop the simulation. All right, and we're going to put this to 20 kilohertz, 20K. All right, and we're going to run the simulation. Okay. All right, and while the simulation is catching up, it does iteration to finally get to a solution. All right, and then now you notice that our angle is closing and closing. So the voltage phase between the source and the inductor is closing into zero again. And that means that the current will be 90 degrees out of phase, right? The current will be 90 degrees exactly out of phase when these things are back in phase. All right, so now, okay, so now we got a problem here. Our millivolt measurement can't measure anymore. It's too small of a scale, so we'll put that back to volts. Rerun the simulation, and hopefully we don't crash anything. All right, and as the simulation adjusts, sure enough, we've got about 60%. Like we said, we got about 60% of the voltage here and about 40% of the voltage here. There you go. So it's doing what it should do. So it's acting as, if we think of these two values just as complex impedances, not complex as in they're complicated, but complex as in they have a real part and an imaginary part. If we think of them as complex impedances Z1 and Z2, this is just a voltage divider, but it's a frequency dependent voltage divider. So that's pretty cool. So the higher the frequency, it passes it better. And that's why I put high pass filter here. Okay. Now, let's go ahead and let's mimic this circuit. All right. So let's mimic this circuit. But since we've already got a high pass filter, why don't we mimic a low pass filter? All right. So I'm just going to show you a couple things. So what I'm doing, you can zoom. You got to go up here and figure out. There's all kinds of tips and shortcuts and the usual. Zoom in, zoom out. F6, F7, all that. But on the mouse, the scrub wheel will zoom in and zoom out like most apps. So that's good. All right. So you can do that. And as far as positioning this, that's not really easy to do. You just kind of have to change the center of zooming, and that's how you kind of can pan around a little bit. All right, so that's one thing that I don't like about this. All right, so anyway, we've got all these icons over here for different things. The first thing that you need to do if you want to kind of build a circuit is you need to get the components to build a circuit. So we need an inductor, we need a resistor, and a capacitor in the previous circuit. So you see here I've got capacitor, inductor, LED, resistor, and actually a 1N4001 diode. How I got those is I press P here. So no matter what I've got selected here on the left, which kind of tool I've got, right? Or excuse me, whatever tool you have selected over here on the left, if there's sub-selections, it'll kind of pop up in this little window right here. All right, so again, it's a Windows program, but it's not as Windowsy as it could be. So if we go to this under the arrow, this is devices. This little triangle looks like an amplifier, component mode. All right, and then we press P, okay, for pick devices. And then you just type in what you want. So we type in, say, capacitor. And again, I don't want to teach you this tool. Capacitor, all right? And then we could find all kinds of different capacitors, but we want is the capacitor primitive for simulation. So we would double click this and it would add into our parts, all right? And then the other part we need is an inductor. And again, we don't want, these are real inductors, and as you click through them, it shows you their footprint and their actual components from actual companies and manufacturers and all these different manufacturers. So we go to modeling primitives again, and then we just pick this one, all right, the primitive for modeling, and we double click that and add that. And we just go through and we would get all these components. Okay, now that we've done that, so now we would just build the circuit. So I'm just going to build the circuit right under here, but what I'm going to build instead is I'm going to build this one, the low pass version of it, okay, the low pass version of it. All right, so I need an inductor here, and I need a resistor here, and I need a source. Okay, so first let's go get an inductor. And I'm going to put the inductor right there. Let's go get a resistor. Click. I'm going to get the resistor and I'll put it here. Okay, I need to rotate the resistor, and I'm zooming in and out with a scrub wheel. So I right click on this and I say rotate clockwise, or I could use num minus minus, like I'm going to remember that. And so me personally, I don't like remembering 8 billion shortcuts. I remember a few of them for compilers and whatnot, but after a while it just becomes overwhelming. So I'm a right clicker. I'll right click on things and try and get a context menu or something that I can do things with, a properties menu or whatever. All right, so we've got this kind of going here. All right, then I need a amp meter and I need voltmeters. All right, so where are those? So again, these icons aren't too helpful. You got to kind of hover over them and figure out. But this is the instrument. It looks like a little gauge right here. And if I click on this, here's all my little instruments. So there's an oscilloscope. So I'll grab that oscilloscope. And then let's see, I need an AC voltmeter. Okay, so I'll put that right there. And then I need an AC ammeter. Okay, and I'm going to put that right there. Okay, so so now let's connect this circuit. So I'm going to click the selection mode arrow, which just makes doing things a little bit easier. I'm going to go like that. I'm going to go like that. And I need a ground, all right? So we could go and find a ground right here in terminals, input, output, bidirectional power ground. And we can put that right there. Another thing we could have done is just left click on anything, and then up here is how you copy things. There's a copy, there's a move, there's a this, there's a that. So if I select something and then click on this icon, it would copy it. Again, I don't want to teach you this. This is a whole class in itself, and we're gonna have our hands full with Circuit Maker. All right, and then AC volts. So I'm going to come here, and I'm going to put this right here. and then I need a ground. So let's just copy that. And so I can also copy to clipboard, and I could paste as well. So I could, you know, left click, right click, and say copy to clipboard, right? And then I could say place and or paste from clipboard, and then there you go. But I don't like doing that. I just like selecting it, and I'll use this block copy. All right. Anyway, so go do that. We got that. Okay, what else do we need? We've got our inductor here. Okay, we need another voltmeter. So now the reason why I like block copy is this. So I'm just going to put a little wire here, and I'll double click, and that kind of ends it. And then I'm going to grab this whole piece here. Okay, so I've selected that whole piece. Then I say block copy, and now you can see why I like that. I can just grab that whole thing. Now I'll take a wire, connect the wire. Now I need an AC source. So again, if you look through here, those are graphs. These are sources, I believe, generators they're called. And so we want sine, and so we can come here and we can say sine, and then we'll connect it, and that's AC source. Oops. So I can select it and change its name to AC source 2. All right. And for now, we'll put its amplitude at 10, and we'll put its frequency at 100 just to start off. All right. And now let's back off. Our circuits are almost alike. We need one more voltage meter across our inductor here so we can measure what it is. So I'm going to grab all this. I'm left clicking and holding it down, and then notice I've got the 4 arrows, which of course means move, and just move it kind of carefully. And I did, and then I click into open area there, and that releases it. And again, I'm going to grab the whole thing, and then I'm going to move it down a little bit. Okay, and now we've got our oscilloscope here, and I'm just going to grab it and drag it in a very Windows-like manner, so that worked for me. All right, then I'm going to come back in here, and I'm going to connect A to the input, and I'm going to connect B to the output, this R2. Okay, and we're all good to go. And then the last thing that I'm going to do now, this is going to really tax the computer running these 2 oscilloscopes. And also, oh yeah, let's name this oscilloscope. Let's go to Edit Properties. So I'm going to right-click on it, go to Edit Properties, and hopefully part reference, yeah, oscope 2. All right, so we got that name right there. And and then we've got high pass filter. This is going to end up being a low pass filter. So I'm going to click that, and then I'm going to say copy. I'm going to drag it here. Then I'm going to double click it, and I can edit it. And then I'm just going to say low pass filter, very Windowsy. All right, and then I'm going to save this. So I'm going to just hit Alt F like you would, and I'm going to say save project as. And then on the screen that you can't see, I'm just going to call this 3. So this is Crash Course EE AC03. In this case, I'm saving it. You can save it as anything you want. Okay, and now it's saved. So now I have this. If this crashes, we can get this. And again, like anything, if you don't have a habit of Control S, Control S, Control S every minute of your life when you're programming or you're developing stuff, you need that habit. Because sooner or later, you're going to lose everything. So I constantly press Control S, constantly. Just saving over and over. All right, so we've got the 2 different things here going. So if we run the simulation right now, it will work. So this is a low pass filter, and so that means it's going to like low frequency. So we're going to get a very high voltage out here when we have a low frequency, 100. So let's give it a try. So I'm going to go ahead and run the simulation. All right, and these oscopes are now in the way, but we'll put them right there. And sure enough, at 100 hertz, we've got, on this one, at 100 hertz, we've got this almost 7 volts, and oh, we forgot our voltmeter over our inductor. Let's get that. We forgot our voltmeter over inductor. So I'm just going to grab this one. I'm going to copy it, and I'll put it right about here, and I'll just click this and drag it a little bit, and then here we go. And remember, we need AC voltmeter here. Okay, Control S, good. Now let's rerun it. Okay, let's move our scopes out of the way. All right, and again, we have 0 volts here. If we could measure millivolts, it would show something. We have 0 volts here, and we've got almost the entire voltage here of the source voltage at 100 hertz, because it's a low pass filter, right? That's just what we would expect. All right, so let's stop the simulation. All right, now let's go to 1 kilohertz. 1 kilohertz. All right, and run the simulation. All right, so now what are we getting here? This is decreasing now, right? So it's a little bit less. And again, we can't really, oh, we made another mistake. What's our mistake? This right here needs to be 2.2 millihenries. So we got to change that, 2.2 millihenries. All right, so let's run it again. And we got another mistake, which I just noticed. So we made a lot of mistakes. So no one's telling me to fix things. All right, this needs to be 200 ohms. Okay, that needs to be 200 ohms. All right, so let's go back, since we messed everything up, and let's go back to 100 hertz and do this again. All right, so 100 hertz, where we wanted to start. And as I said, it's a low pass filter. We're going to get all the voltage over the resistor in this case, because right now this inductor is no impedance at this low frequency. All right, good. We knew that. Even with the mistakes and the values, we're still going to get that. Now we go up tenfold. We go up in frequency tenfold. Now we should start to see some effect of this inductor. And why? At 1 kilohertz, it's about 13.8 ohms. So it's roughly about 7-8% of the resistor value. So we're going to start to see some effect of this. All right, so let's run the simulation. And this will start rising up here. Notice how little current we have inside of the circuit. And again, since we're reading volts here, we're not being able to see much of it. All right, so let's keep going here. Stop the simulation. All right, now let's take it up to 10K. All right, 10K hertz, and let's run the simulation. All right, and something is wrong. And okay, in the United Kingdom, commas are used as periods or dots or decimal points, and so I accidentally put a comma, which I thought would be okay, but it's actually not. I think you actually have to put a decimal point. So again, all right, and again, this is what, and it's hard to see this. You got to be careful. Let's go back to our 100. All right. Okay, let's zoom in a little bit here. All right, let's run this thing. All right. Okay, so we're back at 100 hertz. Okay, now this is better. So we're actually seeing a little teeny tiny bit of voltage, and that's what was bothering me. We just weren't seeing anything here. And so now we're seeing the majority of it here, almost all of it here, and a teeny tiny bit over the inductor at 100. Okay, now things are good. And this is good. You got to make mistakes, and I'm glad I'm making mistakes so that everything doesn't work out perfectly. So now let's go to 1 kilohertz tenfold. But like we said, if we looked at the math here, the resistance is only going to go up to 13.8 ohms roughly, right? So it's not a lot. So it's going to make a little bit of a difference, but not a whole lot. All right, is everything right? Okay. Okay, good. Now, so now look what was going on. Now we're getting, 0.4-ish. It's going to keep rising as the simulation settles. And then 6.67-ish. Okay, good. Now let's really bring it up here. Let's bring it up another tenfold to 10K. All right, bring it up 10K and let's run the simulation. All right. And now we're really starting to see something. So at 10K, let's go back. At 10K, where is that? Right here. That's 138 to 200. It's almost an even voltage divider, right? Almost, right? It's 200 to 138, right? But at 20K, it's 276. So at about 15K, it's maybe around 200, right? We could actually figure the exact value out, right, if we wanted to. But let's just say roughly about 15K, about halfway in between the two, kind of give us about a 200. So let's put it at 15 kilohertz, all right? 15 kilohertz. Let's stop this. And at 15 kilohertz, we're expecting, almost a voltage divider that'll be half and half. All right, here we go. All right, and there we go. So we got both 4 and some change, right? That's good, all right? And then also over here on the AC amps, again, we can't really see that. We don't have enough resolution, so let's put it in milliamps, all right? So we can see what's going on. And there we go. All right, so that is that. So we got the low pass filter, we got the high pass filter, we built the circuit, Control S, Control S, Control S, make sure we got it. This will be, of course, in the resources. And we've got both of these settling to about 5 volts and about 4.85 volts. So now that we have this, let's back off of this. All right, so now one thing that I should have mentioned last time when we were doing the RC version of these, we had our bench and we had hooked the circuit up and we were measuring things and we were having trouble getting accurate measurements with the equipment, right? And I was telling you there's things like, stray inductance, stray capacitance, and so forth, which are all true. But also another thing is the meters themselves only have so much bandwidth to do AC calculations. So a really, really good meter, $200 and above, if it's an RMS meter, it'll be able to measure usually into the kilohertz, an AC signal. But when you think of AC and you think of meters, most meter manufacturers think of AC as AC coming from the wall. And the meters are only good to like 50 or 60 hertz. And they pump it up to something like 400 or 500 hertz it'll handle. So at 400 or 500 hertz, you can measure AC current and AC voltage, and it works. But you need a much better meter that can go into kilohertz or higher, because we're doing things at 10 kilohertz here, right? And if we put a meter on that, it just is not going to work. It's not going to read it right unless you really coerce it and play with it and all that. And so after I did that lecture, I went through all my meters and kind of played with them, and only one of my meters is even remotely accurate and to measure AC up until about 10 kilohertz. All right, so all the other meters are no good. So just to let you know what meter I would recommend, let me put it up here real quick. So Fluke 87. So these are not cheap. These are not cheap, and so this Fluke 87 version 5, this is one of the few meters that actually can measure AC up into high frequencies. Now, these meters brand new are hundreds of dollars. You can find them on eBay for $100 to $200. But if you want to make these AC measurements that we are doing in our circuits at high frequencies, you're going to need a meter like this. There's no way around it. Now, again, you can get them on eBay, and there's a couple models that are Fluke and other manufacturers, a little bit cheaper, but $100 is about the cheapest you're going to get it. Now, let me show you real quick here. Let's go to resources and where you would find this. And this is what engineers do. This is what embedded engineers and electronics and electrical engineers do. We got to just know all this stuff and read about it and figure it all out so that we know what's going on. So here's the data sheet or manual, whatever it's called. I'm going to scroll through here and just bear with me for a second. I know this makes some people sick when people scroll fast. And I'm just going to look for, there's some electrical specifications. It should be at the end. And come in there, okay. And yeah, I think this is what I want right here. Okay, so let me do this slow now. All right, so see this right here, voltage and with the AC signal on there. So it says this is the accuracy. So from 30 to 200 hertz and et cetera, it's this accurate, 1 to 5 kilohertz and 5 to 20 kilohertz. In other words, this will go to 20 kilohertz and you can actually read things, all right? And the accuracy is probably within a couple percent, all right? So that's fine. So that's on the voltage, and then there should be another one. And then here's the remainder of it. And then there should be another one for current. And so that's DC. That's what that symbol means. The bar and the dot, dot, dot means DC. And there should be one for current. Here it is. So milliamperes, all right. And for this is AC current right here, all right. And so it's saying these are again accuracies, and it's not saying what the frequency ranges are for them. Let's see here. This is just the frequency counter. And then here we go right here. Yeah, so, okay, this table right here, frequency counter sensitivity. Now this is the frequency counter sensitivity. In any event, that's what you got to look through, and you got to kind of, parse through these data sheets to figure out what the AC bandwidth of the meter is, what the AC bandwidth of the meter is. And if it's like 400 or 500 hertz, it's going to be useless if you start increasing the frequency to see the response of the circuit like we've done in the simulator. So keep that in mind. So Fluke 87 or something like a Fluke 87 is a good meter to get, all right? And they're up to version 5, but a Fluke version 1, a Fluke 87 version 1 is just fine. The version 5 has got a couple more features, a little bit newer, but the Fluke 87 standard is good as well. Okay, all right, so we're done with this. So now what I'd like to do is I would like to, we're gonna go build the circuit. We're going to build it with a 200 ohms, a 2.2 millihenry. We're going to do the high pass filter version of this. And let's set the frequency at something that the meter can kind of handle. So I think if we go to, let's see, 5 kilohertz, and let's see what our voltages are on all that. Let's run the simulation. Move these oscilloscopes out of our way. And we just want to get two values for the two voltages and a decent current so that we can see something. So 5 kilohertz definitely works. Let's see if we can go a little bit lower. Let's see if we can go to like 2 kilohertz and see if we can get anything decent, which of course we will. And in that case, we're getting less than a volt, so I don't like that. I want to kind of get over a volt. So, all right, let's stick to 5K. So we'll run the hardware that we build up to 5K, and at 5K we should start getting some values that look like this voltage here, this current here, and this voltage here. All right, so 6.6, 6.7, it'll stabilize in a little while, and 33 milliamperes and 2.3 volts here over the inductor at 5 kilohertz. So that is what we want to do. And we're just going to build the circuit with a resistor and the inductor. Exact same thing here, 200 and 2.2 millihenries. All right, so let's go ahead and let's do that now, and I'll meet you at the bench. All right, so we're ready to go here. So we've got our solderless breadboard. We've got our signal generator, which you can take a look there. It's just sitting there waiting. And we've also got our oscilloscope as well. And there's our oscilloscope if we need it. Okay, so I've got all my parts, and so we're just going to put this thing together, all right? So we've got our signal generator. The red is the positive, and the black, of course, is the negative. In this case, since it's AC, it's not really going to matter. It's going to, oscillate back and forth, but just as a reference. All right, so we need a 200 ohm resistor. I looked and I looked, and I am out of 200 ohm resistors, amazingly enough. So we are going to start. We'll put two 100 ohm resistors in series, okay? So if that's okay with you, we'll put one right here, and we'll put another one right here. All right, and okay, so the first thing is notice those leads are different. That's a pet peeve of mine. I'm going to cut those to make those fit because it bugs me. All right, so if I'm going to have long leads, they're at least going to match. All right, so they're symmetrically long. All right, so now I've cut it and I put it in there. All right, now I'm much happier. All right, there we go. All right, so we got our 200 ohm resistor. Now what I'm going to do is I'm going to kind of create a couple lengths of wire here so that I have some space for some instrumentation. All right, so now again, since we're doing inductor circuits, we really want these wires to be short and flat ideally, but I don't have time to make everything flat and pretty, so we're just going to leave them. But when you do this, I'd like you to make everything flat. Just make everything as flat as possible. If you're going to use these boards, which you can do, just make everything flat as possible, and that way it'll work better. All right, and then ideally, if you can put a ground plane under there, so you can do it on one of the bigger metal solderless breadboards, even better. All right, so let's put our positive right here. Okay, so we've got our signal coming into our resistor. We've got a little piece of wire here, and now we're going to put an inductor. So we're looking for our 2.2 millihenry, and we're going to use this component right here. And let me see if I can get the camera to cooperate. Yep, for a second there, 2.2. There it is right there. All right. All right, so I'm going to put this in the circuit, and now this is kind of tough. I got to kind of figure out where I want to put it and remember where these pins are, and they're not very long, so it doesn't stick in there very well. So I'm just going to put it like that. All right, and then now this is going to go to ground. All right, which is not, again, it's not really ground. It's just the reference, which we're going to call ground. All right, and again, I'd like a piece of wire that's not too long. Here we go. This one's kind of good. Let's see. Okay, that's nice. All right. Okay, so there's our circuit right there. All right, let's zoom in just a bit. Okay, there's our circuit right there. So we have our resistor, we have our inductor, all right, and we got our ground, we got our signal generator here. And then now if we want to measure current, we can open this up anywhere and put our current meter in here, right? And if we want to measure voltages, we're just going to take our meter and put it right on top of it. To make that easier, right, what I'm going to do is I'm going to put a couple posts, and that's why I like these little posts. These little posts right here, these little gold posts, which I pull out of sockets. So I'm going to put one, so down here, this is ground, so I'm just going to kind of put one down here at the ground, right? I could touch the meter right here. Yeah, I guess I can do that. I can touch the meter here, but I kind of want it to be close to this. So I'm going to put one right there. And in fact, that's kind of tall, so I want to put a shorter one. Can I find a shorter one? I think so. All right, so there's kind of a ground if I want to do a ground right there. And then by the inductor, I want to put another one. So by the inductor, so I can get a voltage off the inductor. So right there is off of the inductor. So from there to here would be across the inductor. All right, that would be that one. And then across these two would be obviously the resistor. Okay, all right, so I think that's it. There's nothing else to it really, right? We got everything hooked up. We've got our signal generator. We've got the other end of the signal generator. We've got our 200 ohm resistor. Brown, black, brown times 2 is 200 ohms. Resistors add in series. We got our inductor, which is 2.2 millihenries. Now also, truthfully, remember an inductor has some internal resistance. It's made out of a piece of wire. Remember its model is an ideal inductor and a little resistor. If you look up for this particular part, and I think this is either Coilcraft or Worth, W-U-R-T-H, I think its resistance is like 1 ohm or 2 ohms at the frequency, at a certain frequency. So you could add that in the model to be a little bit more accurate, but it's going to be a 1% difference compared to our little resistors here, so we're not going to worry about it. But if we want to be even more accurate, we could go to our simulation and add a little 1 ohm or whatever the resistance is to make that more accurate. Okay, so here we go. So the first thing is, let's go ahead and get the camera on the signal generator here so we can see what's going on. All right, so looking at the signal generator, you see we're at 100 hertz and we're at the 20 volts peak to peak, which if I split this, it's 10 volts and minus 10 volts, all right? So we're gonna get that 7.07 volts RMS, right? So that's exactly what we've got set up. When we do the 100 hertz, right, remember this right here is going to act like a voltage divider. And at 100 hertz, the inductor has no impedance at all. Because it has no impedance at all, we're going to get almost no voltage over the inductor, and we're going to get all the voltage over the resistors, right? So let's do that first, all right? Let's do that first, and because we know that we know that one from memory, all right? So I'm going to get a meter that can actually read this, hopefully, all right? What I'm going to do here is I'm going to back this out and get this so you can see it. Okay, good. All right, and here's our meter. All right, okay. And I'm always torn between doing it like this. Yeah, nah, I think like this. What do you think? Let me back out some more. And this is just always such a pain. You've got all these cables, and it's just a pain trying to get all this stuff, you know, cleanly. So, all right, and if I put it like this, how does that help you? Does that help you a little bit? I don't know. It's still hard to, there we go. Okay, so that's not bad. Okay, so that's what we're going to do, and we're trying not to drag everything off here. So let's put the meter into voltage mode. We're going to put it into voltage. We're going to put it in AC mode here, and we're going to change the range and kind of put it in the middle here. And again, these meters have a little bit of trouble doing this. So if you remember from the math, what we're looking for, let's go look at the math of the original 100 hertz simulation. Where are we here? If we look at the 100 hertz simulation, this is what we did. We had a VR of 7 volts, and then we had a VL of 48.3 millivolts, right? That 0.05, remember that 48.3? And then our current was 35 milliamperes. So we're looking for 7 volts, like 0.05 volts, or 50 millivolts, and like 35 milliamperes. Okay, that's what we're looking for. So let's see if we get anything like that. All right, so we're going to turn on our signal generator. So here we go, turning on the signal generator. All right, signal generator's on. the circuit hasn't exploded. That's always good news. I'm just going to push this in here because, like I said, it's got very short leads. I'm not even sure if it's making contact. All right, so first let's measure the voltage over the resistors. We're in AC mode. We got the right range here. Hopefully, if not, I'll switch it around. All right, and over the resistors. Oh, okay, so the meter, we got to move one of the probes here to voltage. All right, it was in the wrong probe socket. Okay, there we go. And it's showing about 5.5 volts. Let me change the range. Sometimes that gets a little more accurate. 5.7. All right, so we're getting, with this meter at this frequency, we're getting this 5.7. Now let's look over the inductor. So we can go from here to here. This is over the inductor. And we're going to want that decimal place more to the left if we can. That's it. Do it again right there so that we can see this. There we go. And remember, again, these meters are designed for they're designed for higher voltages and they're designed for, fairly low frequencies. All right, so anyway, that's what we're getting out of this meter right there. Let's measure the current. So to measure the current, we're going to have to open up the circuit. All right, so we're going to open up the circuit. I'm going to turn off the signal generator for a second here. Signal generator is off. And now what I'm going to do is I'm just going to open up the circuit like so. And as a matter of fact, let's do it like this. We'll open the circuit up. And then we will put another wire to ground here. And that's where our current is going to dump into. And then we'll put one of our little instruments, one of these guys, in the circuit. We've got to measure current, so we've got to go into the circuit, unfortunately. Then I'm going to take my meter and I'm going to put it into milliamp mode here. I'm going to move the probe into measuring for milliamps, which is right here now instead of voltage. So be careful. I make that mistake all the time. It's hard to remember. All right, then I'm going to plug this in. Again, it doesn't matter which way because we're doing AC. All right, so I'm going to plug that in nice and tight. Okay, so there we go. And if everything stayed connected, let's turn on our signal generator. All right. Okay, and let's change the range here. Okay, and it's starting off on DC, so we got to put that to AC. All right, there we go. And let me play at the range a little bit. All right, and it's showing the current as a little bit less here. Okay, so again, we're getting slightly different readings than our simulation and our math, and that's most in part to this meter. Okay, but now let's increase let's increase our frequency to the 5 kilohertz. I think that's where we had it. Let's take a look at our simulation. And our simulation right now, we've got 6.7 volts, we got 2.3 volts, we got 33.4 milliamps, and I don't think we can open this up while it's running. No, we can't. And we set it at, that was at 5 kilohertz. Okay, so let's just rerun this again. So let's go to 5 kilohertz. So here we go. We're going to go to 5 kilohertz. So I'm going to adjust the frequency here. So there's 100 hertz, and then there's a kilohertz. All right, and then I'm going to go to 5 kilohertz, and the meter probably is really not going to cooperate now. All right, so now we're looking back at our circuit. So now we've got 26 milliamps, so says the meter. The simulation is showing 33 milliamps. All right, and then the voltage across the resistor should be 6.7. So let's see if that's true. So let's pull out the current sense, and let's close the circuit again. All right, so the circuit's closed. Now we're going to use the meter to measure voltage. Let's not forget to move the probe back into voltage and rotate this thing all around. All right, okay, and let's give it a try. So I'm measuring the voltage over the resistors right now, and we're at 5 kilohertz. Yep, we're at 5 kilohertz, so we're measuring over our 200 ohm resistor, and it's showing 5.3-ish. All right, again, our meter is not as accurate as we would like. The simulation is showing 6.6, And over our inductor, the simulation is showing 2.3, and our meter is showing almost 2, 1.9. All right, so again, when you're doing analog stuff, the equipment is important that you're making measurements with. These meters are not designed, unless they are designed, they're not designed to measure AC signals that are much greater than what your AC line frequency would be, which is 50, 60 hertz. And they really do like higher voltages. Anyway, this particular meter can, sort of measure it, but it looks like we're getting like a 3 dB, or we're getting a 30% decrease in the signals. So anyway, when we talk about filters in the next lecture, we will see what decibels are and gains and this and that, and I can kind of tell that we're losing kind of like 3 dB on this meter, which is a small amount. It means we're basically losing 30% of the signal. Anyway, so that's it. So we can see that the circuit is doing what it's supposed to do, and this is a high pass filter, right? A high pass filter. So as we keep increasing that frequency, so if we increase that frequency, and let's just put it up to something crazy like 50 kilohertz. So if we go to 50 kilohertz, and then we go to our simulation, and we stop our simulation, and then we go here to the AC source, and we put this up to 50 kilohertz from the 5 kilohertz, an order of magnitude higher, and we run the simulation again. And then we let these things kind of stabilize. Now over the resistor, we're going to get very little, but over the inductor, we're going to get a lot. We're going to get the majority of it, right? And so now if we go over to our meter here, we can measure that same thing. But again, our meter's bandwidth may be far, far exceeded by this point. So we're going to measure over the inductor here. And our meter, if you can see it, is just kind of floating around right now. And let's see what we get on our meter. So I'm going over the inductor now. And it's showing 6.8 volts, 6.8. All right, that's not bad. And then our simulation, if you go back here, so let's take a look at the simulation. So the simulation is showing 6.8 volts as well. And so over the resistor, it's showing 1.92. So what's interesting is, so at these higher frequencies, this is getting a little bit more accurate, so that's kind of interesting. So over the resistor, 1.86. So actually, it's become more accurate as the frequency has gone up to 50 kilohertz. At the lower frequency, it's not very accurate. So that's kind of interesting anomaly. So with this particular meter, so it does not have a flat bandpass. So the gain across from DC to 50 kilohertz is not flat. It's going up, it's going down, it's probably doing all kinds of weird things. So again, this meter is only a couple $100. I mean, I don't know, $200 or $250. That's not an expensive meter. Most of the meters that I buy will be like in the like this one right here, like $70, $80, and they do a good job. But if you want a really good meter, you're gonna have to pay some good money. So anyway, that's it. All right, so let's go back to the screencast here. So we looked at the RL circuits. We did this low pass, high pass, and low pass. This is an informal look at them. We observed that if we change the frequency in this table right here, then we can see that this thing changes, its voltage divider action. That's the whole point of making a filter. That's how filters are made. So high pass and low pass have these two configurations. We did the math for a single example. We did the simulation. We built the thing, and everything more or less is matching what it's supposed to be doing. So I think you can see these are a lot of fun to play with and using these components. So the inductor is a linear it's a frequency-dependent resistor linearly, and then the capacitor is inversely proportional to the frequency. So you can use those in circuits, and you get two things. One, you get a difference in impedance. Their resistance changes as a function of frequency, and you change the phase angle as well. So that's also useful if you need to do that. All right, so that is about it. And so the next thing that we're going to talk about is we are going to do low pass and high pass filters. and we're going to go into what's called the frequency domain. Right now we've been in kind of what's called the time domain, and we're going to go to the frequency domain, and now we're just going to talk about, instead of saying at one particular frequency, we're just going to say that the frequency is a variable f and it could be all over the place. How does the circuit react in that way? Because what we've been doing is we did transient response with the charging and discharging, right, of this capacitor and inductor. That's transient response as a function of time. Then we did steady state response with these circuits, these kinds of circuits, where it's just at one frequency and it's stabilized. Now we'd like to know, okay, that's great, but now as I change frequency, what happens to the circuit? Is there a mathematical formula that you could write that tells me what the output is? Well, sure. So take a quick look here as a kind of preview. Here's what the current is, right? Here's what the voltage is, all right? So the impedances are going to change as a function of frequency on the reactive component. So this would change, right, which would then change this calculation of VL right here, right? So we could write this math out and we could figure out what this low pass and high pass filters formula is, you know, just using this stuff right here. But we're going to look at a different way to do this, which is a little bit more elegant. And then we can apply it to any circuit you could possibly think of. It doesn't matter. With any number of impedances, 1,000 different capacitors and inductors and this and that, and you just get an equation, you're done. All right, so I'm going to show you that next. So that's it, and so I will see you in the next lecture. Bye. All right, everybody, welcome back. And we had said that we were going to do one of the labs with AC power, line power. And so I thought I would throw in this bonus lecture and we could kind of do that. I know we've spent a lot of time doing the RC and RL circuits and kind of the responses and doing different experiments. But I did want to show you kind of what the things that you have to consider if you want to hook something up to an AC power line and run experiments. So anyway, it's not something that I really want you to do as you're learning electronics because it is dangerous, and even when you're really careful, it can be very dangerous to do that. But I kind of want you to see some of the things that you have to consider. So what we're going to do is we are going to actually build a simple circuit. We're going to build let's build an RC circuit. And what we're going to do is we want to go from AC line power. Here in the United States, that's 60 hertz at 120 volts. So we're going to go from AC line, and this is going to be 120 volts, and that's RMS at 60 hertz. And we're not going to do any calculations here. We're going to use simulation if we want to check anything. And then what we're going to do is we're going to go into a resistor, and then we're going to go across the capacitor. All right, so we're going to have an R value and we're going to have a C value. Okay, now some of the things, so when you start plugging things into AC lines, you really do have to read a lot about this for safety issues and so forth. You have to use capacitors that can withstand the higher voltages, the currents, the temperature, and capacitors that have failure modes that aren't as dangerous as other capacitors. So for example, you know, in this circuit right here, we probably wouldn't want to put just a little simple electrolytic capacitor. We want to put special kinds of capacitors, all right? And so those capacitors are specifically designed to deal with AC signals and higher voltages, higher currents, and so forth, and for operating constantly, right? Okay, so we're going to build a circuit that looks like this, and lots of things to consider when you plug things into the wall. We're going to have a 2K resistor here, and I have a couple capacitors that I want to show you, and one of them is a 0.33, make a better 3 there, 0.33 microfarad and 1 microfarad capacitor, 1.0 microfarad capacitor. And the capacitor that I have for the capacitor that we're going to use in this experiment is called an X capacitor. And there are X capacitors and there are Y capacitors. which are used in AC circuits, kind of in the start of the AC circuit, where you kind of connect to the AC line, and these are used for filtering and different things like that. So they're very safe, and they're designed to be used in certain ways. We're going to talk about that in 1 second. But if we build this circuit right here, and we just take this and we were to simulate this, right, we would get some results. So let's take a look at that first. All right, so we're going to fire up our Proteus, or not. You don't have to if you don't want to. If you haven't downloaded a copy of it, it's free. There's a free copy of it, an evaluation copy. You just can't save. But remember, it's Lab Center Proteus, and just go to labcenter.com and download Proteus. And this file is crash course EE underscore AC underscore 04. It's in the assets for the lecture. So you can just copy it there if you want, or you can build it up. So all we have is a 2.2K resistor here. And let's make sure, got no funny business here. Matter of fact, let me delete this. Let me get another resistor and put it down here. Okay. And we got R1, and we've got this as 2.0K. Okay. All right. And so what we're going to do is we've got an AC source that we've connected it to, and the AC source has an RMS value of 120 volts, and it's got a frequency of 60 hertz. And let's just run this thing. So we go down, we run the simulation. Okay, and we get out of the simulation over the resistor. We've got like 30 volts here dropping over the resistor. And then over the capacitor, this 0.33 microfarad capacitor, we've got 117 volts. And then we've got about 14.6 milliamperes of current going through the circuit. And we know exactly how this works. We've been doing this exact thing. When we hook this up to the AC main lines, this is going to potentially be dangerous. So we want to see how to do that. Now, what we're going to do is we're going to build this on the bench, and then we're going to take it over to some special equipment, which I'm going to show you, and then we're going to run it with real AC coming from the wall. But first, we're going to simulate it, and when we do or we're going to build the simulation, and what we're going to do is we're going to run this at a lower value. So in our case, we can only go up to, our signal generator goes up to 20 volts peak to peak, I believe is the value. Yeah, so it's 20 volts total. So we're going to say 20, okay? And let's run the simulation again. All right, so when we run the simulation again with our 20 volts, and that's plus 10 and minus 10, this particular tool, the peak value, let's see here, so the amplitude, okay, so in this case the amplitude is 10, that's what it likes to see. Then the peak value, the way that this tool interprets peak, means peak to peak. So if the amplitude is 10, that's just the absolute value, so it means it goes to plus 10 to minus 10. So the peak to peak value is 20 volts. All right, okay, fine. All right, and then the root mean square will be 7.07. Okay, so now we've got the correct value in there. And again, you got to make sure you're speaking the same language. Sometimes different tools, different. This is a UK product, and they name things a little bit differently. They spell color, C-O-L-O-U-R. We spell it C-O-L-O-R. Same kind of thing. All right, so we got 0.86 milliamperes, 1.72 volts, 6.87 volts. Anyway, we can run this simulation with different voltages, and we can verify it by building it. So we're going to first build it, then we're going to take it over and run AC through it. All right, so let's stop this. That's kind of what we're doing. Let's go back to our drawing. Now, a couple things. When we are going to play with AC, we're going to first know what we're doing, or we're not going to do it at all. So that's why I say until you really know what you're doing, I suggest you don't do this stuff at all. Now, even when you do know what you're doing, you should be wearing like rubber gloves, you should be wearing rubber boots, and then a couple other things you want to do. If you're going to experiment and play around, you got to be very, very careful with test equipment. And the reason why is if you take an oscilloscope and you hook an oscilloscope up to an AC circuit, all right, you've got two prongs coming out of there, right? One of them goes to ground, right? And one of them goes to hot. If you connect these things wrong to your oscilloscope, you will short it out because the oscilloscope is to ground. So if you connect that ground and you connect it to the hot wire, you'll have a short. So you got to be very careful. So you want to use isolated floating equipment if possible. In other words, you want something that's isolated from the mains, so like a portable oscilloscope or a portable multimeter, right? Another thing you want to do is you want to isolate yourself from the mains. So right now, my mains from my house can supply many, many amps of current, right? These circuits that can supply 10, 15, 20, 30 amps of current. That's a lot of current. A lot of damage can be done. But if we use what's called an isolation transformer, we can isolate the circuit through a transformer so that if something happens, the isolation transformer maybe is only going to supply 1 amp of current, right? So we're separate from the mains themselves. So now what we're going to do is we're going to do something like this. So let's draw what we're actually going to do here. Okay, so what we're going to do is this. We are going to have our circuit here. We're going to have our resistor. We're going to have our capacitor, which we're going to talk about the special capacitors that we like using with this kind of stuff. Okay, and then here is where we're going to put the power in. Okay, now, and we can go ahead and we can put these things here. So this is our R, and this is going to be 2K ohm, and this is our C, and we're going to do 2 experiments, a 0.33 microfarad and a 1.0 microfarad. All right. Now, over here on the left, this is where we're going to connect the line in. All right. So what we can do is we can say, here's, line AC, and here is our socket. All right. And we've got our socket over here, however your socket looks, and we've got our ground here. All right. So this is the ground going to the ground here, and we've got our socket. One of these is hot. All right, one of these is hot. The other one is called neutral. And the neutral is connected to the ground. All right. So we could just connect this just like this. All right. That would be one way to do this, and that would surely work. The problem is if we touch this circuit, we can get shocked, and if something happens, we have the whole line power here powering things up. So instead of doing that, what we're going to do is we're going to use an isolation transformer. So we are going to take this and we're going to put it into a very special transformer like that. And then we're going to have this transformer here. All right. And this is called an isolation transformer. Isolation X-former. All right, and these things can have different values as far as their step up and step down. So this is, in our case, it's 120. So you can have an isolation that could be step up to 240. It could be have a different current that it gives, and all kinds of variations. So I have a couple different products over here. One is a 1-to-1 isolation transformer, and then one is a 1-to-1 and a step up. And I'm going to put them both in there. So I'm actually going to put 2 blocks of isolation. So I'm going to have one isolation transformer, then I'm going to have another one, which is step up and step down. We're just going to use the 120 out of it, but we could have used the step up. All right. Now, the other thing that we're going to do also is, so we've got 2 of these. So let's go ahead and so this would be very safe doing this. Now we're isolated. And then the other thing that we're going to do is we're going to use multimeters, a bunch of meters, right? So we'll kind of draw those here. Digital multimeter. And we're going to hook these up so that we can get the voltage here, like this. We can get the voltage here, like that. Another thing that we're going to do is we're going to actually put a thermocouple. So thermocouple, we're going to make contact here with the thermocouple, and we're going to run this thing over to another digital multimeter. All right, digital multimeter. And this is going to measure temperature. All right, so this is going to measure VR, this is going to measure VC, and we're going to measure temperature. The reason why is I want you actually to see the temperature of this resistor go up very quickly as we're doing this. Now, when we do this experiment, we have to kind of look at the simulation. We look at the simulation, or we could do the math. So let's put actual values in here. So let's go back to RMS, and we're going to put 120 volts. And let's run this. Okay, so this is running and we've got 14.6 milliamperes flowing through here, right? So what's the power over the dissipated over the capacitor? Think about that for a second. What's the power dissipated over the capacitor? Raise your hand. 0. There is no power dissipated over a capacitor. It is a reactive device, just like an inductor. It cannot dissipate power. Now, a real capacitor, of course, does because it has some resistance, right? Because it's not ideal. But for now, we're saying that there's no power over the capacitor, lost over the capacitor. But the resistor does have power lost over it. And what is that power loss? It's either V squared over R, it's I squared times R, or it's V times I, whichever one of those you have. So we've got the current, 14.6, so why don't we square that, multiply it times the resistance, okay? So 14.6 milliamperes, we're going to square that, times 2K. All right, and I get 0.42 watts. If you can see that, 0.42 watts, about half a watt. So that means that's pretty safe, half a watt. The resistor we're going to use is going to be one of those power resistors, one of those big ones. And I think I'm going to use a 2 or 3 watt, so it'll be okay. Then we're going to do the experiment. We're going to redo the experiment, but we're going to use a bigger capacitor, so 1 microfarad capacitor. And when we use that 1 microfarad capacitor, look what happens in the circuit. We get more current, we double the current. And because we're squaring the current to compute power, right, power dissipation, that's really going to increase the power dissipation over the resistor. Let's do that again. 36.2, we're going to square that, 36.2 milliamperes squared times 2K ohms. I squared R is one way to figure out power. That's 2.62 watts. So I think the resistor we're going to use is 2 watt, maybe 3 watt. It should be okay, but it's going to get hot pretty quick. I wouldn't run something that close. I would have a 5 watt resistor, just too close. All right, so that's why we're going to use the thermocouple, and we're going to measure how the temperature goes up on the component. Now, a brief sidebar here. What is a thermocouple? A thermocouple is a device that you plug into your multimeter that allows you to measure temperature. All a thermocouple is 2 dislike metals. When you put 2 dislike metals together, because of their chemistry and electronegativity and various physical factors, there's a voltage potential difference between the 2 metals when you put them together. So when you mechanically put them together and they make contact, there's actually going to be kind of a net charge that's kind of moved around, and you're going to end up with a voltage. So they actually generate a voltage, and that voltage will change as a function of temperature. You can Google it, look up thermocouples if you like. The meters are calibrated depending on the kind of thermocouple, right? There's a few different kinds to measure the temperature based on the voltage. So that's what a thermocouple is. That's how you can measure temperatures, all right? So we're going to measure the temperature. Now, so we're going to run this thing at 120 volts. We're going to do the 2 experiments just like in the simulation. We'll start off with a smaller capacitor because it's safer, because it's only going to put like, what was it, 13 or 14 milliamps. Then we'll put the bigger capacitor, which is going to end up generating more current. But when I do AC power electronics, I don't like just plugging something in even after I've simulated it, even after I built it on the bench. I do not like just powering it up to 120 volts or 240 volts or 270 volts or 480 volts, all these different voltages that are used in AC, right? I like to slowly move my way up. So there's a thing called a variac. And this is a variable transformer. Variac is a variable transformer. And what we're going to do is we are going to, let's find a color here. We're going to, right here, after our, we're going to take our line AC, we're going to have our isolation transformer, we're going to have a second step-up transformer or one-to-one transformer. We're going to isolate it again. Then we're going to put it into a variac transformer, which is going to go right here. So I have these 3 things lined up. Right? And then that variac transformer is going to allow us to go from 0 to 150 or 200 volts or 300 volts, whatever it's designed to do with a knob. All right, so I'm going to show it to you just in a moment, but why don't we just take a quick look here. So if we go in here and we type in variac, we should be able to find some. some nice ones here. So these are what variac transformers look like, and if you've ever seen one, this is what these things are. And so I've got one that kind of looks like this, and a couple other of these. Some of these are really nice, like this $900 one here. Let's click on that. It actually shows the voltage on there. That's handy. All right, but you can kind of get these cheap for, you know, 60, 70, $50. They're not too much, you know, $100, whatever. Some have plugs built into them and so forth. And then the whole point is if we click on this one, Circuit Specialist, I buy things from this company from time to time. So what this allows you to do here is on the left, we put our input voltage. All right, so that's going to come from our isolation transformers. Then on the right, we get our output, and this is nice. It has a nice fuse, it's got a nice on switch, and then it's got a little gauge here. This is an old style analog gauge, which is going to measure the voltage. And then here up top, there's a dial, which you twist around slowly to put the voltage. So we're going to start it off at 0, then we're going to run it up to like 120 volts, right? That's what we're going to do, all right? So that's a variac right there. And if you're going to play with AC, that's definitely something you want to mess with. And the reason why is because it helps you experiment with your AC experiments without just turning the power to full power. You can slowly work your way up and make sure there's no problems because something could explode. Okay, so that's that. Now, let's go back and we were talking about a couple things about capacitors. All right, so I've found a couple links here, and I'll put these inside of the assets for this lecture. But this first one is just a document from Comet, and this is a manufacturer of passive components, capacitors, and whatnot. And it's list file store and you know, a sentence that makes no sense. But it's a nice document, 40 pages about X and Y capacitors. And what I wanted to show you was kind of this. Yeah. So these capacitors, so the X capacitor is used across the line. All right, so that's across, but you know, hot and neutral. Then the Y capacitors are used from line to ground. So if you want capacitors from line to ground for noise, and then you want a capacitor across the input for noise as well, you use these XY capacitors. Now, the X capacitors are across the line. If they short, the risk is fire. Y capacitors go from the line to the chassis, meaning the metal part of the enclosure of the product, usually a appliance. If they short, the risk is shock to the user. In either case, you want to use these special capacitors for those reasons. So these companies make very special capacitors for AC, excuse me, for AC applications called X and Y capacitors. And there's classes of them, X, X1, X2, X3, even Y1, Y2, Y3. And you can read through this and you can just kind of scan through this, and you know, they tell different properties of their different products and all that, but it's still very interesting. And they look like these big rectangles, and I'm going to show you that when we go to the bench. Okay, another, I was just Googling and I found this, justradios.com, safetytips.html. This is actually people who do radio stuff and ham stuff, right? Ham radios, they know an enormous amount about signals and AC and all that, and they work with this stuff, and they work with very high power levels. So they send out watts or kilowatts, maybe even megawatts when they make their radio towers, kilowatts. So they have to know about this stuff because they can get hurt if they don't. Anyway, this is a nice brief kind of little document here. You can just Google and find on internet. It's got some nice links about these different kinds of capacitors. I suggest reading this too. Justradios.com, safety tips, that's nice. And then this is just another distributor, Future Electronics, and that I Googled. And they've got a nice article here, again, talking about XY capacitors and how to use them and the proper way to use them and all that. So what I'm saying is when you build circuits that have AC from the line, when you bring that line in, typically you're going to have some noise reduction and this and that, and that's why we use X and Y capacitors. We're going to use it here in a slightly different way, but it's still, because I know it's a safe capacitor, we're going to use it here, which is kind of across the line. There's a resistor here, right? But this is across the line. So we're using this X capacitor here across the line. There happens to be resistance here, all right? But same idea. All right, and so that's what this article is all about. And you can read this and read the problems and the failure modes and all that, which is really interesting. All right, and there are variacs again. Okay, so that's what we're going to do. Let's go to the bench now and let's actually build this circuit. We're going to test it with the signal generator. Once we've confirmed it kind of works, then we're going to go over to the AC development bench, another bench, and we're going to plug this thing in, and hopefully I don't blow myself up. But I promised you that there was going to be possible carnage. We're going to play with the AC line voltage, and I'm going to show you how to do that. Okay, so let's go to the bench right now and let's put the circuit together. Okay, we're over here on the bench area here where we do our design, and I've kind of started the circuit off just a little bit. And what we've got here is we've just got our resistor, and this is our 2K resistor. Let's zoom in a little bit. All right, we've got our signal generator coming in over here. So let me undo that so you can kind of see it. And I've just got a clip here to measure things. I've got our signal generator coming in here. Now, you can see I'm going to connect the signal generator with these two alligator clips. They are very, very, very close together. I would never do that with AC. It's too dangerous. They could touch and make contact, but since it's a signal generator with very low current, I'm going to get the power in that way. When we go to the other bench, the AC power bench, we're going to do something different to put the power in more safely so we can't shock ourselves. All right, again, you want to be very careful. Right now, I'm not wearing any gloves or anything like that, but I will, and I'll put goggles on and all that. Okay, so we've got our big, you can see here is red, black, red, that's 2K. All right, and this, like I said, I believe this is 3 watts. It's 2 or 3 watts. It's not 5 watts. Anyway, so that's our resistor. We want to have a big enough resistor. Now, let's go over to the zoomed camera. And what I want to do is I want to show you these AC capacitors. So this one right here is, you can see it says X2 on it. And you can read around, it's 1 microfarad at 300 volts AC, and so that's what it can tolerate, 300 volts AC, so we know we're safe at our 110, 120 line voltage. It's an X2, which means it's just slightly higher than an X1 as far as what it can handle, and that's what it looks like. And I've just soldered on here so I could mess around and manipulate this and plug it in. Here's another one. Here's our smaller one. Let's see if we can get a little better contrast. There we go. So this one is 0.33 microfarad. Again, it's an X2. And then we look around. This one can handle 250 volts. So a little bit less voltage, but it'll get it done. All right, and that's what that looks like. Okay, so we're going to start off by putting this one in our circuit. So let's go back to our circuit. Let's pop this in. All right, so we're going to put this in. All right there. Good. And so we're going to make our voltage measurements across the resistor and across the capacitor. We're going to do them with this meter right here. All right, and this will measure AC current and voltage. Now remember, we were having trouble measuring AC current and voltage with higher frequencies, but since this is line frequency, we're going to do this at 60 hertz, we're going to actually be okay. All right, so first what I'm going to do is I'm going to back off this a little bit so you can kind of see everything. So let me zoom back a little bit here for you. All right, so we can kind of see everything. Let me stop that camera from shaking. And do you like that better? No, definitely it's better if it's flat. All right, so there we go, that's nice and flat. Let's get our probes out here. All right, got our probes, we're good to go. We got it on AC voltage, auto. Okay, it says auto DC, that's wrong. So let's go to function. It's on AC. Is that better? And let's put the range. Let's give it another decimal place. Okay. Now we're going to go over to our signal generator, and we're going to set that. And you've seen how this thing works, so I'm not going to belabor setting it up. But I'm setting it up right now for a 10 volt high minus 10 volt low, so it's a 20 volt peak to peak at 60 hertz, and I'm going to turn the thing on, and we're going to see what we see. All right, so I think that's all we need to do. Let's go ahead, let's turn it on. All right, so it's on. Nothing exploded, and we don't expect so because we're dealing with very low power levels here. So let's do some measurements. So across our resistor, let's see what we get. And I'm not worried about getting shocked here. 1.55 volts AC. Okay. And across our capacitor, what do we got? We got 6.9. So we got 1.5 and 6.9. All right, 1.5 over the resistor. All right, so someone figure out what the current through the resistor is. So V equals I times R, so I equals V over R. So we got 1.55 divided by 2K equals, and let me move this over on my calculator a little bit here. and it equals about 0.775, about 0.775 milliamps. Okay, so we got 1.5 and some change. We got 6 point. Let's remember here. It's hard to remember all these things. We got 6.9 over the capacitor, and we got about 0.75, 0.77 over milliamps over running through the circuit, Let's go back to the simulator and let's see what it says real quick, and let's confirm that. Okay, so we're back here at the simulation, and we got the simulation running with the same parameters. And sure enough, take a look. We got 1.72 volts. We had about 1.6. We had about 0.77, I think, was the current, and we got about 0.86. That's great. And we had about 6.9 volts here, and we got about 6.9, 6.87, all within margin of error. And remember, these components right here are models of the components, but there are values for their capacitive, like the capacitor. If this capacitor right here is an ideal capacitor, it's not a real capacitor, so it has no resistance. The capacitor over there does have some resistance, and so on. All right, so now that we've done that, so now what we're going to do is we are going to run the same simulation, and we're going to run it again real quick. Let's put it back up to an RMS of 120. All right, let's go ahead and run the simulation. All right, remember we get, so we get 30 volts, 117 volts. We basically get back the original voltage, and then we got like 15 milliamps, 14.6. Let's keep that in our head. We're going to go build this circuit. We already built it. We're going to go assemble it over on the other bench, and we're going to see what happens. All right, so that's what we're going to do now. So let's go do that. Okay, so the first thing that I want to bring your attention to here is you can see that we have the isolation transformer that I spoke of. This is it right here. All right, and then here's another step up, step down, which we're not using. And then here's another transformer right here, which is kind of hiding behind. Let's move this a little bit to the side here, which is hiding behind the variac, and this allows us to step up or step down. So here's 110 volts, and then here's one step up here, and then this is turned on with this switch here. So we've got line power coming in to our isolation transformer. We switch this on, this then powers this. We switch this on, then this is all powered. So these sockets will then be hot, all right? Now, then we have our variac here, all right? And let's take a look at the variac. So here's our variac, and I'm going to zoom in on this a little bit. So just like it was in the picture, you can see it's got the input there on the left. There's the input. The output is on the right. We've got a gauge here which shows the voltage. All right. Then on top, we can adjust the voltage here with this knob. And then if you look, you can see it goes from 0 to 150 volts all the way to the right if I were to turn it. So I'm going to start it off at 0, all right, and then we can turn it up. All right, that way we ease into the situation. Okay, now moving over here, we have our circuit, all right? So there's our circuit that we're going to work with, all right? And then we've got a multitude of different meters here, which we're going to use to measure different things, and we'll move the camera around as needed. Also, we have a portable oscilloscope. Let's take a quick look at that. So this is a portable oscilloscope. Now what's nice about this is not connected to the AC mains. It's floating completely, all right? So there's no shock hazard or anything like that. So the first thing I'm going to do is I'm going to unplug its power, its charger. I'm going to turn the thing on. I'm going to let it charge, and this is basically a portable oscilloscope. This is a Handtech. It's a DSO 8060. I think this is 30 megahertz bandwidth or 60 megahertz bandwidth. I can't remember. Anyway, so if we want to see something, we can actually do it on here, which is really nice, all right? Then we've got our meters over here we're going to use to measure voltage and temperature and current. And here's our final meter that we're going to use to measure temperature. And matter of fact, it's complaining. So let's put that. So this meter over here to the right has a thermocouple plugged into it, and this is what a thermocouple looks like. Let me see if I can get this in front of you here, so you can see. Let's see if it'll focus. May not. Sort of. It's just a piece of metal, all right, and then it's got this kind of this anti fire resistant sheathing on it, okay? So we're going to use that, and what we're going to do with it is, let's go back to our circuit here. All right, so looking at our circuit, we're going to actually put the thermocouple and put it in contact with the resistor so we can keep track of the temperature of the resistor. And then how we're going to hold it on there is with a little clip. All right, and there's a little clip right there. We're going to hold it on. So that's kind of what we're going to do. All right, so let's go ahead and we're going to kind of start putting this together and then hook it all up. Now, one other thing is I want you to see how we're going to connect the power here. Okay, so here's the Variac, of course. Here's the output. Here's the output cable. All right, and the output cable has these two leads on it. Now everything is off right now, and that's the only reason I'm even remotely touching anything. All right, so we've got those two leads, and then what we're going to do is we're going to plug the two leads right in behind here, and we're going to turn, we're going to make the system hot. All right, the power's not on, so I'm just going to go ahead and do this right now. All right, so now if we kind of zoom into this, if we can zoom in a little bit here and let you see, kind of come down here, and there we go. If the camera will cooperate with us. And the camera is not cooperating with us. Let's put it in manual focus. All right, that's better. There we go, manual focus. All right, so we've got the power coming in here, and then we've got one side of it going through the circuit, back to ground and back around, and then we've got this right here so we can measure if we want, okay? So that's kind of what we got set up. All right, so now let's back this off. Okay, so first thing is, when we're gonna do this, we're gonna put our gloves on. So we're gonna get our rubber gloves. These are rubber gloves, so I'm gonna put those rubber gloves on. I'm gonna put some protective eyewear on, all right? And I've got on rubber boots right now. So rubber-soled boots, and I'm standing on carpet, okay? So I've got lots of insulators. It'd be better if I was standing on a rubber mat, but we're gonna at least put the gloves on, and so that we're kind of working safely. Okay, so then what we're going to do is we're going to do the exact same experiment we did with the other thing. So we're going to turn on one of our meters here, and we're going to put it into AC mode. Okay, we've kind of got things set up here, and it's kind of painful trying to get all these things to fit on here so you can see everything. All right, so we're going to be using this 1 meter right here to measure voltage. We've got it on AC. We've got another meter measuring temperature, and right now it's showing 27 degrees Celsius. Let's switch that to Fahrenheit, if it'll let us do it. There we go, 80 degrees Fahrenheit. It is a little bit warm in this room, I would agree. All right, and so now we've got our circuit set up. We've got our connector here connected where our power is going to come in. So now we're going to turn this whole thing on, all right? And we're going to turn it on slow, and we're going to monitor the input voltage. So what I'd like to do is, first, let's connect the meter to the input here so we can kind of watch this, all right? All right. So we've got our 0.33 capacitor, the lower current version of the circuit, all right? And we've got our meter here, and we've got our temperature thermocouple set up, but we do not have the thermocouple connected. It's just floating in space here, okay? We're going to do that in 1 second. First, I just want to turn this thing on. Okay, so now what we're going to do is I want you to see how I do this. So I inspect everything, I look at everything, all right? I turn my Variac all the way down. It's on 0, I know that. I've got this device is off, I know that, all right? And I've got my isolation transformer right here, which I'm going to flip on. All right, so I've got my goggles. I'm good to go. And here we go. I'm going to turn it on. That's on. Now I'm going to turn this on. Little red light turns on. I notice that this goes over here to like a 120 volts, whatever it should be. And it's, if I can see it down there, it's correct. 110-ish, 120. Okay, so that's good. All right, the Variac is at 0, it's all the way to the left, all right? So now, as I turn the Variac, what we're going to see is, looking over here, we're going to see this change, okay? And the Variac actually has a little gauge on it too, but I don't really trust it. All right, so here we go. We're going to turn the Variac, and as I turn it, I'll tell you where it is. All right, so I'm going to put it up to 15 volts. All right, and you can see that the meter is reading 13 volts RMS. So let me, yep, okay, so that's good. I'm going to go to 30 here on the little markings roughly, and sure enough, there it is. All right, 45. So far, so good. All right, and let's go to 75 roughly. So far, so good. And we're going to put it roughly to line voltage here, which is our simulations at 120. So we're going to put it at 120. All right, so it's at 120. Everything is good to go. Okay, so now what I'm going to do is I'm going to put our thermocouple. I'm not going to touch this while it's hot. I'm going to slowly run down the power. So I'm running down the Variac. Now what I'm going to do is I'm going to turn off. You do it in opposite order. So the Variac is turned off. Now I'm going to turn this off. Now I'm going to turn off the isolation transformer. All right. Now we know there's no power in the system. Now, there is a way to get shocked. Does anyone know how? See that capacitor? It's charged potentially. This capacitor could be charged. So there could be, you know, a couple hundred volts sitting on this thing. So you still got to respect this thing. And if you touch these things, you could get shocked. That's why we wear our gloves. So you got to be very careful. Now, one thing is when you do AC design and you have something coming in to the power, you'll see like a 1 meg or a 10 meg resistor across your X capacitor, that it's across your AC line. It's called a bleeder resistor, and it will bleed the charge on that capacitor in a few seconds, which is helpful. We don't have that, but that's something that you would put. Okay, so now what we're going to do is we're going to put on our thermocouple here, and I want you to show you how hot this gets, how quick it gets. And the reason why this is important is because one of the poorest engineered things is power supplies. People do not do things right with power supplies. They don't measure them, they don't measure the temperature, they don't test them, and then they do their design and then they put the thing in a box. There's no holes in the box, there's no air in the box, and then it gets even hotter in the box, and then the thing fails and starts on fire and your Xbox gets the red ring of death, right? So we don't want that. All right, so what I'm going to do is I'm going to connect this thermocouple, and we're going to try and do some sane kind of something here. So I've been using these little bamboo clips, which are kind of nice, and I'm just going to try and get some good contact here. All right, which bear with me for a second. There. Okay, that's nice. I like that. All right, I'm going to move this over here. All right, because if this touches AC, that would be very bad. All right, so now we've got our thermocouple connected. All right, so now let's go ahead and let's back away. All right, so let's get back so you can see both meters. And I'll just zoom in just enough so you can see both meters and you can see if anything explodes, right? So we always want to catch that on film. All right, so what I'm going to do, I'm going to turn on the isolation transformer, then I'm going to turn on the big step up or one-to-one box, and then I'm going to start sliding up the Variac to our test voltage. I check the Variac, it's back at 0, everything's good, so here we go. Again, double, triple, quadruple check. I got my goggles, I got my gloves on, all right? Here we go. Turning on the power to the isolation transformer, good to go. Turning on the power module here, or voltage regulator, good to go. And now I'm going to start turning the Variac. So right now we got nothing, so here we go. Let's go to 15. Keep your eye on the thermocouple temperature right here, 83 degrees, right? All right, so let's go to 30. All right, 30 looks good. Let's go to 45, looks good. Let's go to 60, looks good. 75, 90, 105, and trying to hit 120. And look at the green meter, and we're at 120. Good, okay? So we're 120, everyone's happy. All right, and look at the temperature. It looks like it's stabilizing. Now, how you can tell, so right now it's definitely rising. So 92, whatever. If you want to make sure that something's stabilized or whatever, go ahead and hit it with some compressed air, and its temperature should shoot back up, right? So right now it's like at 96, and it keeps rising. But let's say it was like, sitting at 96, and my question is it going to get hotter? What I do is just take a quick blast at it with the compressed air, All right, and say I just cooled it down a couple degrees. All right, and it'll go right back up. We just want to make sure it's still thermally moving. All right, so 99, 99, yep, and it's starting to slow down. Okay, so so that's doing that. Great. We know our voltage is 120 on the input, and unfortunately, I don't have a lot of room here, so I'm going to pull this meter out of here, and we're going to start measuring things across these different components very carefully. All right, so while this is on and while this is hot, I am grabbing this, all right, and I'm making sure not to make contact with anything else. There we go, and there we go. Okay, so that's safe. Okay, now I've got my meter here. And what I'm going to do is I'm going to measure this while you're looking at the green meter. All right, so let's measure our capacitor. Excuse me, let's measure our resistor first. Let's do our resistor first here. All right, I'm getting both ends of it here. There's one end and there's the other end. All right, and we've got 27 volts. So at 120 volts here, we got 27 volts. And then over our capacitor, what do we got? We got 117. So we got 27 volts and 117. All right, so let's go back to the simulation real quick. So we're back here at the simulation, and we would just want to take a quick look. And what are we showing here? We're showing we had 27 volts over there. We got like 29 volts. That's good. And then we had 100. I think it was 117 over the capacitor, and it's 117 over here. So let's make sure. So we got like 29 volts on this simulation, 117. Let's go back over to the bench, and let's take a look again. And I'm just killing a little bit of time to let this thing heat up. See, it's at 111 degrees. All right, so again, let's go measure our resistor. And we got like 27 volts. That looks great. And then over our capacitor, we got 117. So this is like dead on correct. This is very, very good. Dead on correct. All right, so we're very happy with that. And our temperature looks like it's stabilizing at the 115 degrees. So that would be okay. So that that resistor could, sit at 115 degrees. That's warm to the touch. It's not going to kill you. It's not going to burn you. And that's where you want to be. You don't want to be up in the 150s, the 170s, and higher Fahrenheit. That starts getting hot. 200, too hot. 100, 115, it's a hot, hot summer day in Texas where we are. That's fine. I can live with that. But anything hotter, we don't want to do. Okay, now let's turn the system off. All right, and then quickly, let's put our 1 microfarad capacitor back in there. Okay, let's do it. Okay, so first what I'm going to do, I'm going to reverse the variac back out slowly. So I'm backing it out down to 0. Did it. Now I'm going to turn off the main power regulator. Did it. Now I'm going to turn off the isolator. Did it. Okay, now let's get our 1 microfarad. Let's put that in there. Right, so I got my 1 microfarad. There it is. Now remember, this capacitor could be charged, right? So I'm going to respect it as if it is. I'm going to put it right there. All right, and then let's get this one in here. And you don't want to drink a lot of coffee and all that when you're doing this kind of stuff. Seriously, you want to have really, steady hands so that you don't short anything. It's hard enough getting this stuff to do whatever you need it to do. These, let me try it from the other way. Let me do it with my right hand. Wiggle this stuff in here. All right, there we go. Okay. All right, that's good. Now what we're going to do is we got to put our meter back so we can measure our variac voltage. We want to make sure it's 120 again. So I'm going to hook this back up into here. All right, so we got that back up in there. Okay, and now our resistor's hot. Let's go ahead and cool it back off. All right, nice and cold, cold air, good to go. Okay, so we got everything, and now let's go back to our simulation real quick and let's see what we're expecting here with the 1 microfarad, all right? All right, so we're back to the simulation, and we're going to put the 1 microfarad in here. We're going to exchange it for this one. So 1.0 microfarad, all righty, and let's run the simulation. We're going to get a lot more current. So we got 36, and then we got 72 volts, and then we got 95 volts. Okay, this resistor is going to get hot real quick because what did we compute? Like 2.4 watts is going to go over this resistor. Okay, so 72 volts and 95 volts is what we're expecting. All right, let's go back to the bench. All right, we're back to the bench. Here we go. We're going to turn on the isolator. We're going to turn on the regulator. I'm going to variac up to 120 volts slowly. Keep your eye on the green meter. Turning up the power, turning up the power. All right, look at the temperature gauge. It's going also. All right, and I'm looking for 120 volts. And I got it. All right, so we got the 120. Temperature is rising rapidly, so let's keep an eye on that. I'm going to undo this meter because I need it. Okay, keeping your eye on the temperature. We're at 130, 140, getting hot, getting quick. All right, so let's measure over our resistor first. Here we go, measuring over the resistor. And we're looking for 70 something volts, so we got 65, and then over the capacitor we got 100. So we got 65 and 100. Look at our temperature. We're up at 200 degrees. So we got 100 over the capacitor, and again we got 65 over the resistor. We're at 215 degrees. Keep your eye on that. Let's go back to the simulation. So we're back to the simulation, and you can see we're showing 65 and 100, and here we go. We got 72 and we got 95. Very close, very close. Let's go back to the bench. So we're back to the bench. We got 227 degrees, 230 degrees. We are cooking that resistor right now. That thing is cooking. That is hot. We could cook on that. Throw some eggs on it. So anyway, we're going to turn the power down now. So I'm going to turn the variac back down. Variac is going back down. Good to go. I'm going to turn off the regulator, and I'm going to finally turn off the isolator. And I'm going to cool down that resistor. So if I touch it, I don't burn myself. There we go. And it's back down to cooler. Okay, we're back here. So anyway, I think that was pretty cool. And you saw the important thing that I want to bring your attention to is we built the circuit, we understand the mathematics of it, we understand the model of it. Then we tested it on the bench with lower voltages. We saw that it was going to work. Then we went over and we did it with AC. We took our safety precautions, but we measured it. We actually took a real-world test and sampled the temperature. We saw that with the 0.33 microfarad, the thing was getting at about 100, 115, 120 degrees. But the 1 microfarad, because the increased current, right, we were getting temperatures up around 250 degrees. So that goes to show you that when you're talking about AC, even a tiny, tiny little current, right, because remember, power is I squared R, can have a big effect on your resistive components overheating. This is a big problem when you do these designs. A lot of times you'll do a design and you'll test it for a few minutes, it'll seem to work, but those resistors are cooking. They're getting very, very hot. Now, that was in open air. Imagine if that was not in open air, if it was closed without proper ventilation and circulation, it would overheat, it would fail, it would explode, it would do something bad. So anyway, that's why I wanted to show you that, and it's a good tip if you're going to do any kind of design, even low-power DC design, anything, be aware of temperature, be aware of heat and all those things because they will destroy circuits and start fires and all those kind of things. All right, so that's it for the bonus round here. So we are going to catch up in another lecture and we are going to start into filters, and we're going to do low pass and high pass filters. All right, so I'll see you then. Bye. All right, welcome to the next lecture, and we are going to continue talking about filters, or rather kind of start talking about filters. So we've been leading up to the ability to describe RC circuits and LR circuits in such a way that we could use the frequency domain. And once we can do that, we can kind of start talking about signals as a function of frequency. So if you recall, just a quick brush up here. So first we talked about the transient response of the capacitor and the inductor, right? And we started to learn how those look like functions of exponential functions, either rising up or rising down, right? And that's when the circuit is powered up first, right? When there's a voltage or a current applied, then we get these exponential transient responses. All right, and then we went over polar coordinates, and we started talking about polar coordinates and impedances and how to describe the circuits in terms of capacitive and inductive reactance, all right? So now we have all those pieces, and where we left off last time was we had described complex impedance, and that of course means impedance that has both a real part and an imaginary part. And we were able to describe a circuit using complex impedances and polar or rectangular coordinates, and then be able to keep these impedances as complex impedances, Z values, and then work those through the various calculations and keep things together. But we were doing it at one frequency. So now what we're going to do is we're going to do this for all frequencies, and this is where things start getting fun. So in reality, very seldomly is anyone going to, compute the transient response of a capacitor or an inductor. Sure, you do it, but more commonly, we're interested in the frequency response of the capacitor or inductor. In other words, as a function of frequency, what does this capacitive circuit do, or what does this inductive circuit do as we change the frequency from DC to infinity, some value in there. And then the thing that we're interested in is to be able to filter these frequencies and select them. So, so you've heard of things like low-pass filters and high-pass filters and band-pass filters and notch filters. These things are descriptive words that describe the different kinds of filters, and we can make these with capacitors and inductors. So that is what we are about to do. So this is going to be, I'm pretty excited now about this. So because we finally have enough math, and again, I don't want this to be a math class, but it's just unavoidable. But you want to learn it one time, and then you can kind of forget about it, but it's really important to understand the fundamentals. So now we have enough math where we can kind of do some calculations and derive some of these filters ourselves. And then later you can just look these things up. And that's what everybody does. There are books like this thick that have nothing but filters in them, all kinds of filters. And then you look them up and you get the resistor and capacitor values and the frequencies that you want, and then you build these things, and there's tools to do it. And we're going to look at some of that stuff also. All right, so let's go ahead and let's just dive right in. And so what we're going to do is we are going to do a few lectures here. And again, I keep doing this kind of university style. I like lectures to be 30 to 60 minutes. I feel that nothing gets explained in 2 minutes. It's just too short, and you can always press pause. If you want to make things shorter, just pause it. So we're going to break this up into a few lectures. So in this lecture, we're going to do RC circuits. We're going to do an RC low-pass filter. And then we're going to go build the low-pass filter, and then we're going to come back and we'll do a high-pass filter, which will go much quicker because we already know how to do it. And then we'll build the high-pass filter, and then we'll switch over to inductors. So low-pass, high-pass, build some stuff, and then move to inductors and kind of do the same thing. Okay? All right, so here we go. All right, so let's see, where are we here? All right, let's pick one of our colors here, and okay. So, let's see here. So the first thing let's do is let's kind of draw a circuit as something that we're going to work with. All right. So what we're going to do is we're going to draw a circuit here, and I'm going to have just a couple components. We're going to have an R and we're going to have a C. And over here on the left, this is going to be called V in. All right, and over here on the right, this is going to be called V out, okay? Now, whenever we have V ins and V outs, they're always taken relative to ground, but just to make that a little bit more clear, we're going to kind of put a ground here, and we'll put a ground here, just so there's no confusion. So we're going to take this voltage V out here, and we're going to take this, do this input here, V in, between these 2 points, right? So it's always got to have a ground reference or some reference, right? Okay, so we've got an R and we've got a C. Now, we know what the impedances of these things are, right? So the complex, so we're going to deal in complex impedance now, and we're going to start writing things in those forms, okay? So let's just go right ahead here, and let's kind of come back to what we recall about this. So for the resistor, we know that it's a completely real component. It has no reactive component to it, right? So if we write the complex impedance, so I'm going to have ZR equals, it's just R plus 0J. All right, remember the R part, this is the real part, and the 0 is the imaginary part, and J is the imaginary number, J or I. If you're an electrical engineer, we call it J. If you're a mathematician, you call it I. Either way, that's it. So if we were to go, let's wait 1 second. We're going to graph this too. Okay, so that's what ZR is. All right, now let's do Z sub C. All right, so now we want Z sub C. And what was Z sub C? If you recall, it has no real part because it's completely reactive, so it's 0, all right? And then it gets a little bit tricky here, but it's minus X sub C times J, all right? So it's minus X sub C times J. So now what is this X sub C? Do you remember what that was? That's the capacitive reactance, all right? We've got to be careful here. So X sub C equals, what does it equal? It equals 1 over 2 pi FC. All right. So in other words, as the frequency goes up, this capacitive reactance changes. So it's a frequency dependent resistor, and it's inversely dependent. And so we can change the capacitor if we want, and that kind of changes the overall size of this reactance. But as F changes, this thing goes up and down. Its reactance goes up and down. So if F approaches 0, so let's pay attention here. So let's say as F approaches 0, so as the denominator goes to 0, right, this whole thing would go up and up and up. So as F approaches 0, X sub C approaches infinity, all right? And now as F approaches infinity, so as the denominator gets very, very large, right, then 1 over something large gets very, very small. So then X sub C approaches 0. So at infinity, this has no reactance, and at 0, it has infinite reactance, okay? And that's why capacitors block DC, right? So if the frequency is 0, that's DC, it's got infinite reactance. So it's, you know, huge resistance or impedance, reactance. And then if the frequency goes towards infinity, then the reactance goes to 0, or the impedance goes to 0. All right. Okay. So now, and then we need to take this value right here, and we need to plug it into this little formula right here. All right. So now we've got Z sub R and we've got Z sub C. Now for a second here, let's go ahead and let's plot these out. Let's kind of remember what this looks like a little bit. So I'm going to create our imaginary graph here. All right, and just briefly plot these things out. Just kind of refresh your memory here if it needs it, but it can't hurt. Okay, so this is going to be the real axis here. So this is going to be plus R, okay? Obviously, the other side is minus R. All right, so minus R. We won't ever have any minus R's, but they're mathematically possible. And they do have meaning, actually, but we're not going to need those. Up here is the imaginary part. The vertical axis is the imaginary part. So we're going to call this the plus. We can call this the plus j-axis. We can call this the minus j-axis. All right. Now, some things to remember is so when we plot a real value, something that's just purely resistive, that's going to be on this x-axis right here, and here it is right here. So this might be our value. This might be our value R right here. All right, and then if we do a capacitive reactance, right, it's negative J, right? So where are we here? It's negative X sub C. So it goes down. So remember, capacitive reactances are going to point downward. And then what was it? Inductive reactances, right? They point upward, a plus J, right? And we're not looking at that right now, but just for kicks. So, and let's write that in a little little bit of a brighter color. X sub L equals, what does that equal? 2 pi FL, right? So remember, x of c is 1 over 2 pi fc, x of L is 2 pi FL. All right, so that is what we are dealing with here. And so this guy down here would be our x of c. Okay, so this is kind of the plot of this in the imaginary plane, all right, in the real imaginary plane, 2D plane, all right, and we've got our two values we've written down, ZR and ZC. So now this is where this gets super cool, and as long as you follow the math, you're going to be able to do all kinds of really interesting things. So now remember when we did voltage dividers, we did a simple voltage divider, right? And a simple voltage divider, let's just draw that super quick, was just something like this. You've got one resistor here, you got another resistor here. Let's call this R1, let's call this R2. You've got ground, you've got some voltage Vin that you put into this thing, and then at this node right here, right, we call that, say, V out, and the question is, what is V out? So remember, V out is just R2 over R1 plus R2 times V in. So it's this thing over the sum of this thing plus this thing, all right? That's all it is. So can we generalize that to impedances? Yes. So now when we're dealing with Z values, right, when we're dealing with Z values, you can write the same kind of equation. So we're going to write this exact same kind of thing here, okay? So this is going to be really useful. So now let's go ahead and let's write this. So now what we want to do is we want to compute V out over here, all right? So I'm going to say that V out equals, what does it equal? Well, V out equals Z sub C over what? Z sub C plus Z sub R. Z sub C plus Z sub R times what? Times V in. Okay, and that's it. So now the Z sub C over ZC plus ZR, this is a very special little thing here. And what this is called the transfer function of this circuit. And so let's formalize that a little bit. If we take the V in and we move it over here like this, and we write V out over V in, and let's close this, get a little bit more room. V out over V in equals Z sub C over Z sub C plus Z sub R. So now what we do is, what we have here is we have the output over the input. So basically this describes how any input, right, will be transformed to the output. All right, so this is called the transfer function. So once you have the transfer function, this function right here, you just multiply it times the input, and that would tell you what the output would be. All right, so we also call this H. All right, and since now here's the interesting part of this, the only variable in the impedance is it's not R, right? It's not C, it's F. So the only variable is F. So the only variable is F. So we're going to call this H sub F. And let me make that purple. H sub F. Okay, so the transfer function H sub F is Z sub C over Z sub C plus Z sub R. That's it. Now, so what does this tell us? This is going to tell us how this simple circuit reacts to a signal, a sine wave, as a function of frequency. So, will it attenuate it? Will it amplify it? Will it, turn it to zero? Who knows? Well, that's what this transfer function is all about. This transfer function tells you that. That's why you want the transfer function. So when you hear electrical engineers talk, analog engineers, you'll hear them talk about what's the transfer function, or the transfer function is this. Once you have that, that describes how the output is a function of the input. That's all you need, and then you're done. You just multiply the transfer function times the input, and you have your result. All right, and then some concept called convolution will come up, but we're not going to talk about that. But convolution is another method of multiplication. Okay, so All right, so now we've got ZC over ZC plus ZR. That's great, but let's run this math down a little bit and can we get an answer that's got 2 pi's, f's, and c's, and r's in it? Okay, so let's give that a try. All right, so I think we have enough room here to do this. Okay, so all I want to do is I want to find ZC over ZC plus ZR. So let's go ahead and do this and start writing things down. Now, be warned, this is algebra. And when you're doing algebra, sometimes you go in the wrong direction and you go off in the weeds and you got to back up and do it again. And we could just look this up in a book, but we're not going to do that. I want you to see the thought process, and I want to show you a couple little tricks to be able to solve these kinds of algebraic problems with some complex math, not complex hard math, but complex meaning imaginary number math to simplify things. Okay, so let's go ahead and let's do this. Okay, so let's rewrite, and I'm going to try and do this sort of small. We'll see. Z sub c over z sub c plus z sub r. All right. So what does z sub c equal? It equals minus x sub c times j. All right, and then let's go ahead and write that. Let's go ahead and write that. Minus x sub c j. All right. Then down in the bottom here, we've got z sub r, which is r plus 0j, and we've got z sub c, which is 0 minus x sub cj. So we can see we got a real part and imaginary part. So we're just going to write that out as r plus a negative x sub c times j. All right. And then if we wanted to, we could just get rid of that. We get rid of that plus, right? That plus is not helping us any. All right. We'll just get rid of that. Okay. And then we'll just make this, oops. We just make this r minus. Okay, so now we got that. So that's pretty good. Now, first thing is we've got these j's in here. All right, we got a j in the numerator and a j in the denominator. All right, so that's going to be okay. But let's see if we can simplify it anymore. And what we want to simplify this thing to, usually, the technique is we want a 1 in the numerator, a 1 in the numerator. So can we get a 1 in the numerator somehow? All right. So what I'm going to do first here is I'm going to use a couple identities. And one of the identities that I want to use that you should remember is this. So let's see if we can remember things. So remember, j squared equals negative 1. Because remember, j equals the square root of negative 1, so j squared equals negative 1. But another interesting identity is 1 over j equals a negative j. All right, so this one is kind of important here. This one's really useful. And this one up here is really useful. All right, so we've got 1 over j equals minus j. So this right here, the question is, can we start getting rid of the j by using one of these identities here and move it around and that kind of thing, all right? So that's what we're kind of interested in doing, all right? So the first question is, can we simplify this? So let's give this a try and see if we can simplify this somewhat, all right? So the first thing that I'm going to do is let's give this a try. And again, you know, I've done this a bunch of times, but each time I kind of do it differently, so you can just kind of see what happens here. All right, so let's go ahead and we can, why don't we, let's get rid of this negative sign first here. So this bugs me. So I'm going to divide everything by a negative first, all right? So I'm going to make this positive, I'm going to make this positive, and then this is going to be negative here. All right, so now we've just got x of c times j. We got minus r plus x of c times j. All right, now why don't we divide everything by j? All right, so that should be fine. So I'm going to divide it top and bottom both by j. So I'm going to divide that by j, and I'm going to divide that by j. All right, so as long as we do j over j, that's just 1, so that's okay. So let's rewrite what we have here. So now we have x sub c up in the numerator. And then down here at the bottom, we've got x sub c minus r j, okay? And now why don't we divide everything by x sub c here? We'll divide everything by x sub c. All right, so let's divide everything by x sub c. All right, and as we divide by x sub c, we're going to get an x sub c here. All right, and then, so what do we have here? Now we've got a 1 up in the numerator. And then we've got x sub c over x sub c, so this is 1. And then we've got minus, and then we have r over j times x sub c. So we've got r over j times x sub c here. Okay, So this is looking pretty good. And so now this is kind of a little bit messy here. So let's see what we can do with this. So now at this point, why don't we go and take our x of c and let's plug in what the value of x of c is, all right? So let's just kind of flip this around. So now we're going to have 1 over 1 minus r, all right? And then we're going to have j down here in the bottom. And you should, if you're good at math, you can already see where this is going. So x of c is 1 over 2 pi fc. So when I write it here, it's going to come up in the numerator of this fraction. So this is going to be 2 pi fc, okay? And then we've got our j right here. And now, so we've got, this is really 1 over j, 1 over j. So what's 1 over j? 1 over j is the same as minus j, all right? But I've already got a minus there, so that'll flip it to a plus. So that's cool. So we got 1 over 1 plus, all right? And then now I'm going to collect this right here, 2 pi frc. 2 pi frc, right? I'm going to just grab those things together. So 2 pi frc, all right? And then this whole thing, remember, there's really, you know, a little 1 there, right? So it's 1 over j turned to minus j, and minus j times the minus is plus j. So then there's just the j right here, or right at the end. So let's just, we'll scooch it in right there, and then let's just rewrite this one more time in a different color. And a matter of fact, let's put it someplace else. So let's put it right here. Is this good color? Yeah, sort of. All right, so let's put it right here. So this h sub f, right, when we're done with this, so we're going to say that h sub f equals 1 over 1 plus j 2 pi frc. All right, so this is our transfer function of this circuit. All right, so now let's just think about this for a minute here and take a minute to just kind of breathe this in. So what did we do? So first what we did was we said, hey, this is just a voltage divider. And then we said we know what complex impedances are, and we know how to write resistors and capacitors in terms of complex impedance. So we did that. First was ZR and here was ZC. Now once we had complex impedances, the rules of voltage, all the rules stay the same if you use Z's instead of R's. So we basically said, okay, what's V out? V out would be Z sub C over Z sub C plus Z sub R times V in. Then we said, well, this whole thing here, this is an abstraction called the transfer function. And to get that, we can just put this V in over here. Now we have V out over V in equals Z sub C over Z sub C plus Z sub R. This could be anything. And we call this, in the abstract, H. And it could be H of T or H of S or H of F. And in this case, it's H of F because this is the variable F, the frequency. And then we went and we just started doing algebra. So we just did algebra here. This is just, you know, algebra. And sometimes this works out, sometimes this doesn't, all right? And we did some algebra and we got lucky, and as this simplified, it simplified to 1 over 1 plus j 2 pi frc, all right? And then we wrote it down over here, so here's our final transfer function, all right, h of f, and that's it. So now, what this tells us, the j in here is a little bit confusing, but just for now, hold on to your horses and forget about it for a second. But it looks like as the frequency goes up, or the frequency goes down, this value is down here in the denominator, right? So as the frequency goes up, this transfer function is 1 over 1 plus this mishmash of stuff. So no matter what, as the frequency goes up, this value is going to get bigger and bigger and bigger. So 1 over a big number is going to become a small number, all right? And then vice versa, if f gets smaller and smaller and smaller, 1 over a small number is going to get big. So the transfer function of this circuit right here, all right, is going to be such that it's going to end up being what's called a low-pass filter. All right, so this is a low-pass filter. So let's go over that again, and let's see if we believe ourselves. So this is a low-pass filter. Now this is going to get a little bit tricky right here. There's a subtlety that confuses a lot of people. So I don't want you to get confused by this, and I want you to really understand this. So we're going to go over this to make sure that you do. Okay, so here's the subtlety. So remember that a voltage divider works like this. So if we're going to take the voltage right here over this node, and I'm just going to reiterate that node is where V out is taken. if the voltage drop over this this device here, which happens to be a capacitor, is very large, right, compared to the voltage drop over this R, right, then the output voltage would be closer to the input voltage. So for example, say we put 10 volts into here, and then we got 9 of those volts out of here, and then only 1 of the volts dropped over R, then that means that this V out right here is 90% of the signal. So in other words, since we're taking V out from this node here on top of the capacitor, as the impedance of this branch gets large, the voltage over it becomes large over. A big impedance means a big voltage drop, right? If the voltage drop is big, that means it mimics what the input voltage is. So even though the capacitive reactance action, right, is making the impedance big, you would think, oh, we're getting a small signal out. But no, because we're dropping a voltage over it, right, we get a large signal because of big impedance, right? So again, to make an example, if this was 1K and this was 100K, right, and we put in 10 volts, I'm going to get like, right, 99 volts over this right here, right? So it would be, what would it be exactly? It'd be 100 over 1 plus 100, and those would all be Ks, right? So it'd be 100 over 101, right, which is 0.99. All right, so we would get 99% of the voltage times V in, right? And that equals V out, right? So, but we're not talking about pure resistors here. We're talking about a resistor and a capacitor. So this is weird, right? Because the capacitor changes its reactance and its overall impedance as a function of, frequency. And the transfer function, when we look at this like a voltage divider, but not with an R and another R, but with an R and a C, what does it look like? It looks like this thing. So this thing is what happens, all right? So this function right here is what happens. Now, here's where things get a little bit tricky, and you have to be able to compute this properly, all right? So now what I want to show you is, so how do we figure out what the magnitude is? Because this J here is a little bit confusing. So let's see, can we get rid of the J and just figure out what the magnitude of this output is, just the magnitude of it, all right? And then if we have the magnitude, then we can just multiply by the voltage and we get an actual voltage. Okay, so let's do that. So let's just go ahead and let's just erase some of this over here, give ourselves some room. And I think I'm going to, yeah, we really don't need all this algebra stuff here, right? So let's move this, all right? And we've got our result over there, so we already know what that is. And let's get rid of this little thing here. We already kind of did this, and we've got our, that was just our little voltage divider, so we don't need that. Okay, so now let's go ahead and let's take this transfer function right here. All right, and so what we want to do is we want to find the magnitude of H sub f, all right? So we want to find the magnitude of it. So now let's refresh our memories what we mean here. So we want the magnitude of this. So if we were to put magnitude around this, what does this mean to doing, what do we do to the thing on the right here, all right? The magnitude of this. So that's what we want to figure out, the magnitude, all right? So we want to find the magnitude of H sub f. Okay, that is horrible writing. Let me try that again. Magnitude of H sub f equals question mark. That's a horrible question mark. Okay, not too much better. So how do we compute magnitude? Let's go over here for a second because this is going to kind of help us with this. All right, let's use, I got some gray colors here. All right, so let's say we've got our X sub c and we've got our R here, and we want to find our magnitude. Now, do you remember what we do to do that? All we need to do is compute the vector, and what vector is that? It's this vector right here. And if you draw this in here, let's try and draw that straight-ish. And it is a lot harder than you think to draw on these graphics tablets while you're looking at the screen and drawing on the tablet. It's not easy. Okay, so we want that length right there. And do you remember how we compute the lengths? Remember how we do these length computations? It's just this. It was the square root of the square of the real part and the imaginary part. So in this case right here, in this graphic, it would be the square root of r squared plus x sub c squared. That's it. That would be the length, and we could call this length, let's just call this length, we'll call this the length of this thing here. which is just the length of that, right? We could just call that z. Just in this case, we just call it z. That would be the length of that. So over here in h sub f, how do we figure out this? All right, so this is the exact same. So what it is this. So let's just use a different color here. Let's use this pretty cyan, I think. All right, so let's get rid of this. All right. The numerator, what is the length of the numerator? So the numerator only has a real part, so it's 1 squared square root, which is 1. Okay, so I'm done with that. The denominator has a real part and it has an imaginary part. See the j? So there's the real part. So this is the real part, and this is the imaginary part. Okay? So that is the two different components. So let's just square each and take the square root. So here we go. So what is the real part squared? Well, that's just 1 squared. All right. And what is the imaginary part squared? Well, that's just 2 pi FRC squared. All right. And that's it. And then this, let's just bring this down here and simplify a little bit more. So we've got 1 over, all right, and then we have the square root of 1 plus 1 squared, of course, just 1. And then this, there's not much else we can do with this. This is just 2 pi FRC. Okay? So that is what we have for the final magnitude of the transfer function. So again, that is the magnitude of h sub f equals this right here. So now notice there's no more j in there. So if we then take an f value, any frequency value, we plug in the r, we plug in the c, we'll actually figure out what this number is. Then if we take that number and multiply it times v in, that would tell us what v out is, right? And that's all there is to that, okay? So now let's go ahead and let's talk about some of the aspects of these transfer functions and some of the terms that go along with it, all right? So let's do that now. What I want to do here is let's give ourselves a little bit more room, maybe. I think we can write right here for a little bit. So, okay, so a couple terms I want to bring your attention to are these. So now let's take a look at what happens to this function here, right? And this is the magnitude of the transfer function. Let's take a look at what happens to this at some special frequencies, all right? So what happens if this right here, okay, see this is 1 over the square root of 1 plus this, and there's a squared in there. I am glad I just caught that, all right. Okay, so what happens if this term right here, all right, what if this term becomes 1? Okay, so let's see, can we make this term 1? What would that do to this overall transfer function magnitude? Okay, so that's kind of interesting. So we're just going to take this term here. We're going to say 2 pi FRC, and there's a square there, squared equals 1. All right, so now let's get rid of the square. So I'm going to take the square root of both sides. All right, so I'm just going to take the square root of both sides. All right. And then, so what does that give me here? That gives me back 2 pi FRC equals 1. Now let's compute this as a function of f. So let's find the f that makes that true, right? So basically we're just going to divide everything by everything but the f, right? So then we're going to get f equals 1 over 2 pi RC. So now this is a really little interesting little piece of math here. So this f equals 1 over 2 pi RC, this right here is special because if the frequency that you run this thing at equals 1 over 2 pi RC, all right, then this filter is going to have a special kind of behavior, right? And that behavior is this. So let's go ahead and let's plug these numbers in here. So we're going to plug this this value in for f here, all right? And let's see what pops out of this. Okay, so we're going to say at f equals 1 over 2 pi rc. What do we get? All right, we get 1 over this thing we're plugging this all into. Okay, so let's go slow here. I don't have anyone to correct me. 1 plus 2 pi rc, and then when f equals this right here over 2 pi rc, right, then we're going to replace this f right here. So then look what happens here. This goes down here. We get 2 pi rc, and we get the whole thing squared, equals 1 over, again we get 1 over 1 plus, well this is just 1, 1 squared is 1, so we get the square root of 1 plus 1, which equals 1 over the square root of 2. All right, this is really actually quite important, so let's take a second here. 1 over the square root of 2, all right, so if you go ahead and you compute what 1 over the square root of 2 is, let's go ahead and let's do that. So 1 divided by the square root of 2 equals 0.707, right? And that's that 0.707 again. So in other words, 70% roughly, so 0.707. So this is really, really important here. All right, so now let's go ahead and we'll go right up here. So 1 over the square root of 2 is approximately equal to 0.707, all right? Now, so here's the thing, at a frequency of 1 over 2 pi rc. So when you put a frequency that is identical to the product of rc, right? So 2 pi rc, 1 over that, if you input a frequency of that, then the output of this filter equals 70% of your input because the transfer function goes to 70%. All right. This value here, this f equals 1 over 2 pi rc, all right, this is called the corner frequency or cutoff frequency, corner or cutoff frequency, and it's the frequency that this behavior starts happening at. So we're going to draw a little graph right here, all right, and okay, so here is frequency on the bottom. All right, and then the vertical axis is h sub f, magnitude of h sub f, all right? So when the magnitude of h sub f hits 0.707, right? So this is what this thing looks like. So this is a low pass filter. Let's use a different color here. So we go, and then this thing starts cutting off like this. This value here, right, where this starts cutting off, and let's draw this a little bit better, sorry. And we're going to let's draw it with blue here. When it gets to about here, and when we go over here, and this value is 0.707, all right, when this is 0.707, this value here, this F value, right, is called this F cutoff frequency, right? And that's when this filter is appreciably working. So electrical engineers just kind of say that at this value, this thing, the output is at 70% of the input, and then it's going to keep getting less and less and less and less and less. So this is very important. So you'll hear people say, set the cutoff frequency for some frequency. That means at that frequency, I know that the output signal is now at about 70% its input. And then as that frequency keeps going higher or lower, depending if it's a low pass or high pass filter, the attenuation will get greater and greater, and the signal will die more and more and more and more. Okay, so now we have a lot of knowledge here. So we know how to model a low-pass filter with a resistor and a capacitor. So all you need is a resistor and a capacitor. We know that the transfer function looks like this right here. We know that h sub f looks like 1 over 1 plus j 2 pi frc. That's what the transfer function looks like. Then we know the magnitude of the transfer function looks like 1 over, here's better, 1 over 1 plus 2 pi frc squared. That's the magnitude, and that's what we care about. So now we know that, okay, so this describes the circuit action. So if we put a sine wave in the input, a sine wave of any frequency, as the frequency changes, as f changes, this is super important, as f changes, this thing changes what it does, and this is super cool. This is what a filter does. So as f changes, this thing changes. How does it change? By this function right here. And even though it looks a little bit nasty, believe me, it's pretty simple compared to really nasty functions. So this is how it changes. Now also, put a pin in this, the phase of the signal also changes. So as you have the input signal, and I'm just gonna, let me put it right here. So let's say that we were to look on an oscilloscope, and let's say that the input signal was red, and it's a sine wave. All right, and let's say that the output signal was blue. Okay, so now not only does it attenuate, right? So here would be like the attenuation as it gets filtered, right? Not only does it attenuate, but it also shifts. So it also shifts in phase. So the phase of this thing actually changes. All right, so the phase of this thing actually changes too. In this phase angle, we could figure that also. So remember, here's the transfer function. It's got a real part and imaginary part. If we wanted to, we could figure out the tan inverse of the real part, of the imaginary part over the real part. That tells us the phi. That tells us this phase angle between here, that these things are shifting. So the output also gets shifted, and this is important. Now let me tell you why this is important. Say you're making an audio amplifier and you put in a frequency and it amplifies it, but the output is amplified or attenuated, and but it shifts the phase of the signal by some value. Now you put in another frequency and say it amplifies or attenuates that, but it changes the phase of that in a different way. So now what's happening is all the components of the sound that were all in lockstep, all these different frequencies, they're getting shifted around in phase, which causes distortion. It's phase distortion. So that's important that you consider that also. But we're not going to get into that. That's a little bit too advanced, so we got enough to deal with on our plate right here. Okay, so all right. So we have our transfer function. We've got what our low-pass filter looks like. So now let's put some real values in here real quick before we get to doing our actual board work, circuit board work, and do this. So for example, if we had R and C both equal to 1, then this transfer function, what would it look like? The magnitude of the transfer function, it would just look like 1 plus 2 pi f times 1 times 1 squared. So it would just be 2 pi f squared, 2 pi f squared. So then as we put f in here and say f was 0, if f was 0, then we get 1 over the square root of 1, which is just 1. So at a frequency of 0, we get no attenuation, right? We get no attenuation. Now, as we keep putting larger numbers in for f, we get more and more attenuation, right? And then we could sit there and compute those values for a simple value of R and C both equal to 1. 1 ohm and 1 farad, which would never happen. So typically, we're going to use values of like R equals k ohms or hundreds of ohms, and C is going to equal microfarads. 0.1 microfarad, 0.01 microfarad, 10 microfarad, that kind of thing. And then we want to solve for this. Okay, so then the question becomes, all right, great, this is really cool. I want to make a low-pass filter, and I want it to pass everything up to, say, some frequency, right? And I want it to start cutting in at some frequency f. Well, that's where this thing is right here. So you see this f equals 1 over 2 pi RC? So what we do is we use this backwards. So we say, given a frequency that we want this thing to start cutting in, compute 1 over 2 pi RC. All right, so let's take a look at that now. So let's go ahead and let's erase. I think we can erase this stuff right. Why don't we erase all this? We don't need this anymore. Up here, let's erase this. Okay, so this is really cool. Okay, so now the thing is, say someone says, hey, I want you to make a filter that starts cutting in at 2 kilohertz, and I want it to start cutting in at 2 kilohertz and then attenuate the signal. Okay, so you say, okay, I can do that. So what do? We go get this right here, this formula right here, which describes the cutoff frequency. All right, so it says F equals 1 over 2 pi RC. Now, one thing is we haven't learned how fast this thing starts cutting in, all right? Now, in electrical engineering, this would be called a one-pole circuit, There's one reactive element here. So there's one pole, it's called. If there's two reactive elements, it would be two pole. So the more reactive elements, the steeper this transition happens, the steeper these attenuations are, right? But since we only have one, it's not that steep, right? And what I'm going to do is we are going to talk about, as a matter of fact, we're going to have to, we'll stop this and we're going to do one more lecture before we go to the circuit board development, and we're going to talk about decibels because we need to know that. But I want to stop this because I don't want to cloud this up. All right, so let's go back here. So we say 2 kilohertz. So we know that our cutoff frequency formula is this for this low-pass filter design. We know that we want this thing to turn on at 2 kilohertz and start cutting this thing off. So we want it to pass everything from DC to 2 kilohertz and start turning on. Okay, so then we put our 2 kilohertz in here. So we put 2 kilohertz equals 1 over 2 pi RC. But wait a minute, we got a little bit of a problem here. We've got two variables. We've got R and we've got C. Pick one and fix it. All right, so this is a solution space. So this is a two-dimensional solution space, but we can pick one and then turn it into a one-dimensional solution space. So we pick something that we can control, that is harder to control. So resistors are pretty easy to get any value in the universe, but capacitors not so much. So we don't want to pick a resistor and then get some bizarre capacitor value. So let's fix the capacitor value in this solution space of RC, right? We'll fix the capacitor and then we'll find solutions only on R, okay? So why don't we pick something that we know we have a lot of? So I know that I have a lot of, let's say, 0.1 microfarad. Okay, so now we've got 2 kilohertz equals, and you can see how fun this is. It's just like, it's like a mathematical mystery, but it all connects very slowly and carefully and methodically, and it's just a lot of fun. All right, and then we have R, and then, you know what, let's draw R in a different color because we're going to solve for R. And then we have our capacitor here, C, which we know is 0.1 microfarad. Okay, so what we're trying to figure out now is R. So now we can turn this around and put this in terms of R. So let's just do some algebra. So I'm going to, move things around. So why don't I move R to this side? Equals, and then I'm going to move the 2K to the other side. So we're going to get 1 over 2 pi, and then this 2K is going to come down here. So we got 2 pi, and then we'll just put 2K hertz here. And then we've got our capacitor here, which is this 0.1 microfarad. All right, that is what our R is. So let's go ahead and let's get our calculator out. So we'll do 2 pi, 2K, 0.1 microfarad, and invert it, right? Okay, so we've got 2 times pi times 2 kilohertz times 0.1 microfarads. And what do we get? We get, and then invert that, 795 ohms. All right, so we get 795. So R equals 795. And because we're going to be dealing with like 1% or 5% resistors, we can just round this one way or another. So we could call this, something like 800 ohms, all right? And then if we were going to do this circuit, hey, and if we only had a 1K ohm resistor in our parts, use 1K, right? So let's say that we did. Let's say that we only had a 1K. We don't have an 800 ohm. Sorry, we don't have it. So let's say that we actually have a 1K ohm, okay, 1K ohm. Resistor is all we got. So let's plug this back in. So if we plug back in, so what is it? So F equals 1 over 2 pi RC. So let's plug in our actual values. So into R, what are we going to plug? 1K. Into C, we're going to plug 0.1 microfarad, and we're going to compute what the actual cutoff is with the values we actually have in our lab. All right, so let's do it. 2 times pi times R, what's R? 1K, times our capacitor, which is 0.1 microfarads. Okay, and invert this. It is 1591. All right, so now the value is, instead of this, we get 1591 hertz, or 1.59 kilohertz. So, so what we've done is we've created a filter that, with our actual components, that is going to start cutting in at 1500 hertz roughly, and then start attenuating from there along this curve. All right. The steepness of this curve, all right, the steepness of this curve is basically this formula right here. It's a 1 over curve, right? So it's a 1 over curve. But it's also measured, you can measure it in a thing called decibels, all right? And we're gonna stop the lecture here, and we're gonna pick it up in another lecture, and we're gonna talk about decibels briefly, because this is a huge confusion with people. But just briefly, in case you're gonna take a quick vacation, a decibel is, we're talking about things in orders of magnitude of 10. In electrical engineering, we don't talk about things linearly because they just don't change fast enough. So we talk about things in orders of 10, 10, 100, 1,000, 10, 1, 0.1, 0.01, etc. So when we talk about filters, we talk about decibels or decibel gain or attenuation in orders of 10. So when is a thing going to be 10 times as amplified, 100 times as amplified, 1,000 times as amplified? When is it going to be 1/10 as amplified, 1/100th, 1/1000th, right? Because typically we're talking about signals that are so small or so big that we don't really care about 2s and 3s and 4s and 5s. I care about 10s and 100s and 1000s and 10,000s and 100,000s and millions. I want to make things real big or real small. So we use decibels, and I'm gonna show you that in the next lecture. So this is a lot, a lot of math, but we learned a lot: low pass filter, transfer function, magnitude of the transfer function. Then we learned how to figure out the cutoff frequency or corner frequency, and that's this F right here. That's when the thing starts operating. So right now you know enough to make a low pass filter. If you put a sine wave in this thing and sweep the sine wave from 0 to whatever, you will actually see the sine wave. It'll be full magnitude, not attenuated, and then it'll start going like that. And then what we want is to make it go really quick. So as the frequency hits that cutoff, we want it to fall off like a brick wall. So coming back to this transfer function thing, we want to have the transfer function look like this, and it just go boom, straight down. So like right when it hits that transition, we want any of this slowness. This is how many poles. So when you get to like a 7 or 10 or 12 pole filter, this thing is literally like a brick wall or a cliff. It just falls off it. It just boom, instantaneously. It's like the signal's there and then it's gone. But that comes at a cost of complexity, and you have to do it with what are called active filters. You can't do it with passive filters. It's just a train wreck. But passive filters mean there's no amplification or active circuitry. You can get a 1, a 2, a 3 pole filter pretty good, and you can do a high pass, a low pass, a band pass, and a notch filter, and save money. It's going to be a little bit sloppy and a little bit slow, but hey, that's okay, and that's how a lot of television sets used to work, and so forth. Okay, so I think we're good. Our hour's up, so I will see you in the next lecture, and we're going to briefly talk about decibels and a little bit more math, and then we're going to go to the bench and we're going to build this low pass filter. All right, so that's going to be a lot of fun, and maybe we'll blow something up. I don't know. All right, I'll see you later. Bye. All right, welcome back. We are on the next lecture, and we just talked about low-pass filters. And as you can see on the screen here, I kind of erased all of our math work and just left our filter up. And the next thing that we're going to do is we are going to build something on the bench. But before we do that, we need just a little bit more, not math so much, but a concept and some terminology so that we can use this in discussions. And I didn't want to blend it into the discussion of the low-pass filters. So what we're going to talk about is the concept of what's called a decibel. All right, so let me write this down here. Decibel. And you've probably heard this term before, or have even used it roughly, or you may even know exactly what it is. In any case, a decibel is, deci is a tenth of a bell, and a bell is a unit of measure that's used in electronics, named after Alexander Graham Bell. And let's see here. What I want you to do is, if you go to Wikipedia and you type in decibel, you'll get this page right here. And I'd like you, this is a really long page, it's got a lot to it. I'd like you to just read the first part of it, which is kind of the history and the definition, which is what we're going to talk about. We're going to talk about this definition here. All right, so decibel is a logarithmic unit, and so that's important. We're going to talk about that. And then there's a couple, so decibels are typically used to measure relative quantities or gain. So it's something related to something else. So one value related to another value. So it's a ratio. However, if we want to use a reference or a standard, so when someone says something is so many decibel, it really doesn't mean anything unless you know what the reference is or you know that it's a ratio. So so there's two things that are usually referenced, and one is a dBm, and that means that it's a power reference, and we're talking about 1 milliwatt. So 1 milliwatt is what the reference is. So if something is 10 times stronger or 100 times stronger, it's 10 milliwatts or 100 milliwatts. That's what we're talking about with dBm. It's relative to 1 milliwatt. Now, dBV is relative to 1 volt RMS, all right? So 1 volt root mean square. So when we're talking about gain or voltage gain, we would be saying that the reference is 1 volt if we say dBV. If we don't say dBm and we don't say dBV, then we just say dB or decibel, then typically it's just a ratio we're talking about. All right. Now I'm going to show you the math of this in a second, but I just want to show you some of these numbers over here to the right. So forget the power ratio stuff. So if something has a dB gain of 0, that means its ratio of amplitudes is 1, all right? So if the output over the input, so remember our transfer function, right? Our transfer function, if the output over the input is 1 and there's no attenuation, no gain, then the dB of that would be 0. So we're going to see how that works out. And now let's go and, for example, let's say what would be if something were to gain up 10 times, right? So if the voltage gain were 10, so here's voltage gain 10, and then if you look at the dB, it's 20. So that's interesting. And then 100 is 40, 1,000 is 60, all right, and then 10,000 is 80. Likewise, if we go in the opposite direction, now this is where it kind of gets interesting, and the math will bear this out. If something is 1/10, so here's 0.1, it's minus 20. If it's 0.001 or 100th, it's minus 40. And if it's 1/1000th, 0.001, it's minus 60 dB. All right, and then there's some special, very commonly used dB gains. And those are when we have something that is, see this minus 3 and the plus 3 dB? Look at these numbers. So look at this number right here. 0.708, that's really the 0.707, right? So that's our square root of 2, 1 over square root of 2 number, right? And then here is the square root of 2, 1.414, and a bunch of decimal places, which they've just truncated to 1413. So the point is that remember when we were talking about the transfer function, we talked about the cutoff frequency of the filter, and when the filter got down to 0.707, which was 1 over the square root of 2, 0.707, that's 3 dB. In fact, it's minus 3 dB. So when the transfer function or when the output is minus 3 dB, that's what we call the corner frequency, and that's where these numbers come in as 0.707 and a bunch of fractional components, or 1.414 and a bunch of fractional components. That's plus and minus 3 dB. That is that corner frequency. So when you've gained down from, you've got a gain of unity, right? So there's no attenuation in the passive filter. When it drops to 70%, right, that is minus 3 dB, all right? And that's where that comes from, all right? So now, and there's also a page, if you go to a gain underscore electronics in Wikipedia, and this is kind of just an excerpt. This portion right here is just an excerpt of this longer page when we get down to the math, which is right here. All right, so I want to just show you this, and then we're going to go and do the math ourselves. So what I want to do is I want to show you right down here. So if we're talking about gain in decibels, what it looks like is this. It looks like the output over the input, and it's 20 log base 10 of that, all right? That is kind of how we compute a voltage gain. Now, let's go to the gain page. So there's two different gains here. One of them is gain dB when you're talking about power. So it's 10 times the log of P out over Pin. all right? And if you're talking about voltage gain, come down right here, it's 20 log the output over the input, all right? And the reason why it's 20 log is when you kind of go through the math here, it's V squared over R, right? That's power. So it's V out over V in, and then there's a square here. And then if you know how to work with logs, whenever you have an exponent here, you bring it out and multiply it as the coefficient of the log. So this 2 comes out here, all right? So bottom line is this, and again, you just read through this and try and remember it, but if you ever want to do power, compute power logs or power dV, it's 10 log power out over power in. That's how you do it. If you want to compute voltage gain dV, then it's 20 log the voltage out over the voltage in. All right. Now, this is an actually interesting little statement right here. This simplified formula, the 20 log rule, is used to calculate voltage gain in decibels. Okay. And is equivalent to power gain if and only if the impedance at the input and output are equal. In other words, if the impedance seen going into the system is the same as going out of the system, then what'll happen is the voltage gain and the power gain will actually be equal. The gains will be equal because when you run through this math, they'll be the same. So you can always figure them out separately, but they'll actually be the same if the impedances are the same. And that is something we're not going to talk about, but it's called maximum power transfer. And to have the maximum power transfer in a circuit, you can figure this out, but if you've got one block moving into another block, you want to match the impedances. So you want the output impedance of one block to match the input impedance of the other block, and when you do that, the power, you'll have the maximum power transferred. So when you have an amplifier circuit, for example, if the impedance is small and this impedance is large, you've got a mismatch. You won't have maximum power transfer. Likewise, if the impedance is large and small, you won't have maximum power transfer. When they're equal, then you'll have maximum power transfer. Now, when they're like this or like this, you may have a larger current or a larger voltage, but to get maximum power transfer, you want them to be the same impedances. All right. Okay. So let's go ahead and let's do the math. Okay. All right. So here we go. So let's start here. So let's write again what our transfer function was and a couple things for this low pass filter, just really quick. So we figured that we called it H sub f equals 1 over 1 plus j 2 pi FRC, right? And then that's equivalent to V out over V in, right? V out over V in. All right, and both of these, everything is a function of f. Here's that f inside of there, which is a frequency, all right? And then we computed what the magnitude of h of f was, right? Because we needed a real number. We wanted to get rid of that imaginary component there, right? And what was that? That was 1 over, and let's see here. It's 1 over, we're going to take the squares to the real and imaginary part. So that's just 1 plus 2 pi FRC quantity squared, and that's all under that radical. All right, so we could compute the gain. All right, so now you recall that I was saying that we have another important little value here, and let's put that, let's put it right here. And we had this thing called the cutoff frequency, And this cutoff frequency was, what we did was we said, well, what if we make this radical, if we make this right here, what if we make that a 1, then we're going to get 1 over the square root of 2, and 1 over the square root of 2, 1 over the square root of 2, right, is 0.707 and some change, right? Let's just do it just to make sure. So we'll take the square root of 2, we'll inverse it, all right, and we get 0.707106781, 0.707 and some change, okay? So now that is an interesting value because we get this 0.707, which is basically down 30% or it's at 70%, whichever way you want to look at it. That's called the cutoff frequency. Now, this cutoff frequency means that the signal coming out of this filter or this device or this block is roughly 70% of the signal in. So that's kind of where we feel like this filter is starting to work, right? And this is just a convention. but it's also minus 3 dB, okay? This now, a few moments ago didn't really mean anything to you, minus 3 dB. Now, from that chart that I just showed you, minus 3 dB equals 0.707. All right, so now we see where this dB stuff is important, because remember, when we're talking about filters and amplifiers, we don't typically care about if something's amplified 1 or 2 or 3 or 4 or 5. We want to know, is it amplified 1 or 10 or 100 or 1,000 or 0.1 or 0.01 or 0.001 attenuation. So we like to do things in orders of magnitude, and that's typically how circuits are designed, in orders of magnitude. All right, to do that, we need a logarithmic scale. All right, and now those of you that are not familiar with logarithm or forgot it or never learned it, haven't learned it yet for some of our maybe junior high school students that are watching. So let's take a look at that and take a little segue and look at log, and then we're gonna show how to do this dB stuff, and then we're done, and then we can move on to the bench. Okay, so let's talk about logarithms. All right, and so logarithms, okay. All right, so all logarithms are is a way of dealing with powers of values in a simplified form. So everyone kind of knows how to do this. So if someone were to say, you know, what's 10 to the third power, right? What's 10 to the third power? Well, that's just 10 times 10 times 10, all right? So the 10, this is called the base, right? And this 3, that's called the exponent, right? So we know how to do that, right? And so in computers, we deal with binaries, so it's a base 2 system. So if I said, what's 2 to the 8th, right? 2 to the 8th would be, anyone? 256, right? Okay, and so, and just as a little side note, if you do deal with computers, it's really helpful to have these things memorized, you know, so and here's another little thing. Anything to the 0th power is what? Is always 1. Anything to the 0th power is 1. So 10 to the 0 is 1, 100 to the 0 is 1, anything to the 0 is 1. Okay? All right. And you should really have, so if you're a computer person, you should really have these powers of 2 memorized, you know, so, you know, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16384, 32,768, 65,536, 131,072, and so on. All right, so you should have those things memorized so that you can do bit manipulations in your head, at least up to the powers of 8, which is 2 to the 8th is 256. And let's check that on our calculator. So 2, and then your calculator should have an exponentiation function, which looks like x to the y usually, to the 8th is 256. All right, okay. So all right, so that is normal exponentiation. We all know how to do that. Now, let's do something a little bit tricky. So now, what is 10 to the minus third? What does that equal? All right, well, this is just over 1 to 10 to the third. So you just invert it. So whenever you have a minus exponent, it's equivalent to 1 over the base to the positive exponent, okay? So this is then equivalent to 1 over 1,000. All right, same thing here. If we have 2 to the minus 8th, that's equivalent to 1 over 2 to the 8th, which is equivalent to 1 over 256, all right, which is a fraction, which I don't have that memorized. All right, so, you know, if someone were to say, what's 2 to the negative 1, that's 1/2, right? And why? Because it's 1 over 2 to the 1, and 2 to the 1 is 2, which is 1/2. All right, so those are some of the rules of logarithms, and you can go and learn about those. A couple other interesting little rules is if we have the same base, so if you've got 10 to the third times 10 to the fifth, you just add up the exponents. That would be 10 to the 8th, okay, with my horrible 8. All right, if you don't have the same bases, then you have to change bases. But if you have the same base multiplication, you add, all right? And if you have the same bases, 10 to the 9th divided by 10 to the 5th, then you subtract, equals 10 to the 9 minus 5, which equals 10 to the 4, okay? So those are some of the rules there. So now, those are logarithms, those are exponents, standard exponents. Now we can ask the counter question, and the counter question is, so 10 to the third is 1,000, All right, so now let's go ahead and let's just keep this up here so you can see it. All right, so let's use a simple example. 10 to the third equals 1,000. All right, so now we've got this thing called logarithm, and where does that come in? All right, so given 10 to the third equals 1,000, we might want to say, what's the log of 1,000? All right, so what's the log of 1,000? Okay, so the log of 1,000, now log typically means, it's unspoken, that it has a base of 10. All right, so it has a base of 10, log of 1,000, base 10 equals 3. All right, so now this is kind of where this gets tricky. So 10 to the third equals 1,000, but the log of 1,000 equals 3. So what log really means is 10 to what power equals 1,000? The third power, right? So you can see here that all this really is, that's where the 3 is, that's where the 1,000 is, and that's where the 10 is. All right, so it's just a different way to write this so that we can kind of, instead of dealing with 10 to the third equals 1,000, we say what number, 10 to what number equals 1,000. All right, and then we can work with logs instead. All right, so now let's write this down with some numbers here, or with some definitions. So this is the base, so log base. All right, and then I'm going to call this, let's see what I want to call this. I'm going to call this y, and I'm going to call this x. All right, so log of base, and instead of base, let's call it b. All right, so this statement here would be read, log base b of y equals x. Log base b of y equals x. Now, typically log is always base 10, so it's implicit. We already know that it's 10, so we'll just say log y equals x. But what it really means is this. What does this really mean? This is equivalent to, it means b to the x equals y. All right, and then this connects back this whole exponential format of things. All right, okay. So now that we have that, so now so logs are, what we want to do is we want to figure out 10 to what power equals the log of the number. 10 to what power equals the log of the number. All right. Okay. So given that, then what we do is we come up with this thing decibel, and we say, all right, this thing has got a gain of 20 decibels or 40 decibels or 100 decibels or 60 decibels or minus 3 decibels. What does that actually mean? Well, what it actually means is this. So let's talk about voltage gain here for a second. So we're going to talk about voltage gain. All right, and so that means this. So we're talking about gain dB, so we're going to say dB, all right, equals 20 times the log of V out over V in, all right, and then that's it. And I'm probably covering up my little thing here. So let's go ahead and let's move some of this stuff over. Actually, let's go up here. Let's move this over. And let's put this up here so we got some room. We don't need this 2 to the 1 thing here. Let's just get some space to work with here. Okay. All right, so let's come back up here. So we're going to say voltage gain, and so voltage gain dB equals 20 log V out over V in. Okay, all right, and we'll just erase this, give ourselves some more room here. All right, and I want to put this right here. Let's put this here. B to this is equivalent to b to the x equals y. All right, give ourselves some nice room here. Okay. Okay, so let's write this out. So let's say that we have someone told us that we had 20 decibels of gain. So let's say gain in dB. What is that equal to? That's equal to 20 times the log of V out over V in. All right, and now someone tells us that, oh, this circuit, it's got a 20 decibel gain. All right, so it's 20 decibels. Okay, so someone says, hey, this is equal to 20 dB. All right. So now the question is, what was the actual voltage gain, all right, if it was equal to 20 dB? Well, we can go cheat and look at that, right? We can go back to our table, which I think is here. And 20 is an amplitude ratio of 10. All right. So it's an amplitude ratio of 10. But can we compute that? So let's go ahead and let's compute it. All right. So let's pick a different color here. Okay. So basically, we know that our formula looks like this. It looks like 20 log of V out over Vn, all right? And so we're looking for this ratio V out over Vn, right? Equals 20 dB. All right, so now let's just do some math here. So we can divide both sides by 20, that's fine. So we'll divide both sides by 20, they just cancel out, right? Okay, and then we have the log of V out over Vn equals 1 dB here, all right? But what does this really mean? And there's really a 10 here. So it means 10 to this value here equals this value right here. So 10 to the 1 equals V out over Vn. And remember, where do we get that? We get that from over here. That's what this really means. It means b to the x equals y, b to the x equals y, b to the x equals y. So this is like equivalent to x, and then this thing here is equivalent to y, and this thing here is equivalent to the v, the base. So 10 to the 1 equals v out over vn, and 10 to the 1 equals what? 10. All right, so that tells us that if you have 20 dB, the voltage gain is 10. Let's go back and look. 20 dB, the voltage gain is 10. Aha, that's cool. Okay, so now let's go ahead and let's see what that minus 3 dB value is. Okay, so let's get a little bit more tricky. So let's do the minus 3 dB. Okay, so someone tells us that the gain in dB, equals minus 3 dB, which we know equals this thing, 20 log, and V out over Vn, all right, V out over Vn. I'm just going to write this time as V out over Vi, VO over Vi, okay? So we know it's this right here, so now can we manipulate this and figure out what this value was right here? Now we're not going to be able to figure out exactly, we're going to get a decimal, but you'll see why I want to do this. Okay, so let's come over here and write this down. So we've got minus 3 dB equals 20 log of V out over Vn. All right, so let's divide both sides by 20. Divide both sides by 20 here. All right, and then we have minus 3 over 20. So we have minus 3 over 20. We're just going to leave that. Log of V out over Vn. And again, so what does this mean? It means there's a little imaginary 10 here, not imaginary 10, but there's a little 10 there. As convention because it's base 10. So this means that 10 to the minus 3 over 20 must equal this voltage gain V out over V in. All right, so if we can figure out 10 to the minus 3 over 20, that'll tell us what this ratio is. Okay, so let's go ahead and get your calculator. So we're going to do 10 to the power of, and then what you want to do is depending on your calculator and how good you are at your calculator, be careful. So we're going to do 10 to the, and then we're going to do minus 3 divided by 20. All right, so in my calculator, I'm going to do 10 to the power of, and then I'm going to put in parentheses negative 3 divided by 20. All right, and then look what value I get. Can you see that right there? So I get 0.707. What's that 0.707? 0.707, so this equals, so V out over Vn equals 0.707, and we know that 0.707 is equivalent to, is the same, equal to 1 over the square root of 2. And 1 over the square root of 2, we know that that's the gain of our low pass filter. For example, when we put off the cutoff frequency, and when we put the cutoff frequency of, nope, spelled that wrong, cutoff. When we put the cutoff frequency of f equals 1 over 2 pi RC. When we put that frequency in for f, we'll end up with a gain of 1 over the square root of 2, or an attenuation of minus 3 dB. Okay, so The point of all this is that decibels help us describe the gains of amplifiers or filters or the attenuation of an amplifier filter. If it's a positive number, that means it's being amplified. If it's a negative number, that means it's being attenuated. If it's 0, that means the gain is unity, which is 1. And you can look at that from the table. You can run through this math if you want and kind of prove this stuff to yourself and get a feel for it. A lot of people memorize this stuff pretty good now. I actually figure it out in my head every time. I don't know why I don't memorize this, but I always have to think back to the definition. So like a dB of 20 means it's a gain of 10, and then a dB of 40 is 100, and dB of 60 is 1,000, and then minus 3 is, you know, the 1 over the square root of 2, then you know, minus 20 is 1/10, and minus 40 is 1/100th, is minus 60 is 1/1000th. For some reason, this table just doesn't seem natural to me. I don't know. So either way, memorize it or understand the math. But this is how we derive this. So now, when I say something has, you know, it's about 20 dB, you're not going to be like, what is he talking about? You'll at least know this is a logarithmic gain, and you can go look it up or you can figure it out. You can figure it out, and then the answer is, oh, he means it's a gain of 10. Why don't you just say a gain of 10? You could just say a gain of 10, and a lot of people do. A lot of people don't talk in dB; they talk in, you know, just decimal gains, right? That's fine too. You can do that too. However, electrical engineers, people tend to use decibels and logarithmic scales because they make some other things nice and clean. For example, that chart that we made, that transfer function chart, if you remember that graph, and we'll finish with that. Let's just go ahead. Let's just erase this stuff right here. If you remember that transfer function where we kind of wanted to show things as a function of frequency, these are typically logarithmic. So in other words, when you see one of these graphs here, like this, you'll see gain up here, all right, and this gain just may be a decimal gain, right? And then you'll see frequency down here, and then down here might be 0 hertz, right? And then here's 10 hertz, and then here's 100 hertz, and then here's 1,000 hertz, 1 kilohertz, and then here's 10 kilohertz. So you see, the scale is linear, right? The ticks are linear, but each time they're 10 times more than the previous, all right? So then when you graph these things, what these things will look like is they'll do this kind of stuff. And when we're talking about a low-pass filter, a single-pole low-pass filter, we know that this point right here, right, when we come over here, this is that 0.707 mark, which we call this the cutoff frequency, right? And this is when this filter is starting to actually do something appreciable. We call that the cutoff frequency. In the case of this filter, it happens to be this value here, 1 over 2 pi RC. And then by graphing it like this, the curve of this curve right here ends up being minus 20 dB per decade. All right, so and then if it was 2 poles, it'd be minus 40 dB and so forth. So the whole point is it's just a convention used, and it makes things look a certain way. And whenever you look at anything online, you're going to typically see things in these logarithmic scales. And then there's logarithmic paper. There's paper that's actually graphed in logarithmic format like this. Okay. All right, so that's enough of this. So if we see the word decibel, we know how to deal with it. We know what it is. It's important to know this, at least go through it once in life. And so then when someone says, you know, it's for example, they'll say it's a 100 dB gain, and like 100 dB gain, and you're like, well, 100 gain, that doesn't seem like too much, right? But if we go look at, it's 100 dB, that's 100,000 is the actual gain, not 100, but 100,000. So 100 dB is 100,000. So that means that is a really powerful amplifier. Then on the other end of the spectrum, right, with negatives, if you look at negative 100, right, that means 0.00001 is the gain or attenuation. So it's tiny, tiny, tiny. So typically you'll see positive numbers when people are talking about amplification. That's a good thing. You'll see negative numbers when they're talking about attenuation or they're talking about filtering. So when something's got like, it filters at minus 120 dB, that's really, really, really good. Or the signal to noise ratio, right, is like 100 decibels or minus 100, depending on the interpretation of it. The whole point is we want a value that's very, very tiny or very, very large, and that's why decibels. So instead of us saying it's 100,000, they'll just say 100 dB. And it just helps you because things tend to operate in powers of 10 when you design electronics. Okay? All right, so I think that's it. We've got everything we need. And so we're going to stop here, and then we're going to go to the bench, and we're going to build the the low-pass filter, this R and C, and we're going to start off with values of R like 100 and 1K and values of C of like 0.1 microfarad and 1 microfarad, and then we're going to look at the response of it based on our analysis with the oscilloscope, and then also with this cutoff frequency here. So let's remember this. This is really important. 1 over 2 pi RC. We can always plug our values of R and C in here and see what our cutoff frequency. So I'm going to leave this up, and so we can keep going back to it in the next lecture. So let's stop here, and then we're going to go to the bench. All right? Bye. Okay, welcome back, and we are on the next lecture, and we are going to build the circuit that we've been talking about, the low-pass filter. So to refresh your memory, all we're going to do here is we're going to have an R, a resistor, and we're going to have a capacitor, and this very simple circuit. So we're going to have an input at one end, and we're going to have an output at the other end, and just basically an R and a C to ground. And be very careful, because if you put the C where the R is and the R where the C is, we're going to have a high pass filter. And we're going to look at that next, of course, but right now we're doing a low pass filter. All right, so we know that our cutoff frequency is this 1 over 2 pi RC. All right, and so let's take a look, if we use some common values, what we think that our cutoff frequency is going to be. We'll calculate it, and then we'll go to the bench, and then that'll give us a frame of reference. So let's say, for example, we do, let's say that R equals to 1K ohms, and let's say that C equals, say 0.1 microfarad. All right, so if we plug those values in, let's go ahead and let's erase some of this dB gain stuff. We don't need this anymore. I like to keep what's up here on the blackboard for each lecture so you can kind of remember things, even though you can just look at it in the video. All right, so now what we're going to do is we're going to plug these values into this formula right here. All right, so F equals 1 over 2 pi. There's always a 2 pi in here. All right, and then R, and what's R? It's 1K. Okay, so 1K ohm. And what's our C value? It is times 0.1 microfarad. All right, so let's go ahead and plug that into our calculator. So we've got 2 times pi times 1K times 0.1 microfarad. All right, and then we're going to take the inverse of that, and then we get to 1591. So it's 1591 and some change, but we're just going to call that 1591 hertz. So this is important. This is in hertz. So this is approximately equal to 1.5 kilohertz, 1.5, 1.6 kilohertz, right? So that's going to be the cutoff. So ironically, I mean, I drew this curve almost exactly correct. So if we put a 1K and a 0.1, this curve right here, let's use this color here, this curve right here that we're showing the response is exactly what we should see. So basically, here's 1.5 kilohertz as drawn. Actually, that's where we should see that 70% or that minus 3 dB. All right, now as we change these values, as we make R or C different, then this 1.5 kilohertz is either going to go up or go down. All right, now since we're dividing, it's 1 over that value. So if we make R bigger right? So if we make R bigger, this would be smaller. If we make R smaller, this would be bigger. Same thing with C. So once you have a reference point, the 1.5 kilohertz, then we can play with R and we can play with C, and then we can see what happens, all right? Now, we're going to not simulate this inside that simulator, but I really want to quickly show you that it's very easy online to find tools to do low pass and high pass filters so you don't have to build them or build a simulation. So if you just go to Google and you type in low pass filter calculator, there's many of these online. People make them in Java. It's when you're learning a program, it's a fun thing to do, is to make a little simulator that just does that calculation. So I went through them, and as a matter of fact, I think I already have this page. Yeah. So here's one on Aqua Electric Design. They've got a low pass and a high pass filter under filter tools. If you go to filter tools, there's RC filters, LR filters, RLC filters, and you just put Salin key. These are active filters. So that's one of my favorite kinds of filters. Lots of filters. So this is a really cool page. So sim.okawa denshi.japan JP/English and then fkeeson.htm. Anyway, I obviously I'll put this up inside of the materials. All right, so what do we want? We want an RC low pass filter. All right, and here's our transfer function. Right, so there's our transfer function. We've seen this before. It looks very similar to ours. It's got an S here though, and S is what's called the S domain, and basically S replaces J omega with this value S, and it's done with a Laplace transform, and that's something we don't need to know about, but it's called the S domain. It's very similar to the frequency domain. But anyway, we don't really care about that. All we care about is there's an R and a C. It looks just like ours. And let's go and put these values in here. So let's go put 1,000 ohms, and we're going to